What's up? We got Rat in the audience. What's going on, dude? Can you hear me, Rat? Yeah, is the audio working? Sometimes when like Discord does start events, like audio doesn't work for some reason. Does the audio work? Lol. Okay. One sec. Where's okay. All right, does it work? Does it work now? Yeah, see, that's some weird bug with Discord. Anytime there's an event and I start it for some reason, well, I'll stop the music, sorry. Anytime I start an event, it shows the audio like playing, like it's green on my side, but no one in the audience can hear it. I don't get it. Like, Discord, fix your stuff, man. Fix your stuff. Yeah, super annoying. Indeed it is. What's up, Rat? Are you a high school student taking AP Physics? No? Oh, you're just here to chill? Well, that's cool. You want to learn some physics? We're going to do some physics today. Yippee! Yeah, nice. Yeah, we like physics. I got my my PhD in physics from UCLA. I did plasma physics. That was my stuff. And then now I teach it. So I run a nonprofit as well, teaching kids math and science on like Twitch and YouTube. And I what was it? This Gohar group, I guess, had a call out for AP Physics review teachers, and I was like, oh, cool. Like, I do that all the time. I teach a lot of AP Physics, so I was like, yeah, sure. I'd be more than happy to run a quick review session with you guys. Or not quick. It can be 2 hours. I don't care. I mean, the next one I got to do is AP Physics 2, which, what time am I doing that one at? Let me see. Oh, that's it at 3 p.m. All right, so it's 11 a.m. my time right now. Next one is at 3. This is a pure physics review session because I need it. Yeah, you got it, Jadathir. You're here. Jeff, you need to stream, dude. Yeah, so we're also streaming this on Twitch. So, yeah, if for whatever reason you don't like watching things on Discord, you can also watch it on Twitch. Just keep in mind there's a little bit of a chat delay with how it works. Yeah, AP test tomorrow. Is calculus tomorrow? No. I think calculus isn't until... It's interesting. So AP calculus and AP physics C, I think, are on the same day. Because I have a couple students who are taking the... Or you have AB. Yeah, I think it's BC and C. So BC Calc and Physics C are on the same day. And so they're having to... So you can take like the makeup one, which is like a week or two later. I've seen that as well. Yeah. You guys had an AP Calc review, right, too? Yeah. Well, here's the cool thing. I mean, like, some of the physics... Well, okay, AP Physics 1 doesn't really touch any calculus because it's more of an algebra-based course. But in AP Physics C, if we were going through that, I could maybe answer some calculus questions as well. But, yeah. Okay, cool. Let me give people, like, another, like, 3-4 minutes to, like, trickle in, and then we'll start going through... my plan for today was to go through the FRQs from 2023 because I think that's what students have the most trouble with is going through FRQs. You let me know if there's something specifically where you're like, hey, Dr. I don't get this. Like, can you explain some more stuff about, I don't know, like angular momentum or conservation of energy? We can do that as well. We'll probably cover it in the FRQs. The FRQs tend to cover all the topics that need to be. You love the bedazzled mic? Thank you. Yeah, it's fun. Physics, my favorite. Yeah, physics was my favorite. Yeah, I out of all the science, I took a lot of the APs in high school. I took AP chemistry, AP biology, AP physics, AP CS. You guys have like 2 computer science classes now. It's like AP CS principles and AP CS something else now. But in my day, it was just AP CS. And yeah, out of all the sciences, I was like, I like physics the most. So that's why I went and did it in undergrad. And then after undergrad, I really liked plasma physics. So that's why I went to UCLA for grad school. And then I did my PhD in plasma physics over there. So, and then after that, I was like, cool, I want to get out of academia. And so now I teach it, is what I do. So, but not as like a formal teacher, or not a formal teacher yet. I don't know. I may get tempted to that eventually, but I try to do as much as I can on like Twitch, YouTube, Discord, TikTok. Yes, we can go over to work after the FRQs. Yeah, 31 people. Yeah, cool, nice, great. Tension force, all that stuff. Yeah, so feel free. I will try to watch the chat as much as I can while I'm going through things. Try to keep it mostly related to. I know some people love to just be keyboard warriors in the chat and just discuss whatever, but try to keep it kind of clean, involved with just physics stuff, so I can answer as many questions as I can with that. And if whenever we're going through the FRQs, you're like, wait, I don't get that. Please, yeah, just, you know, you can even like raise your hand if you want to speak on the stage. You know, just don't get me into trouble, please. But we can slow down and go through anything that doesn't make sense. Yeah, cool. Pulley questions. Yeah, oh, torque and inertia. Yeah, I know those. Where like the pulley isn't massless. Yeah, that's always the worst, dude. You're like, no, I don't want that. Yeah, they try to mess you up with that stuff. Okay, cool. All right, let's start it off. All right, welcome everyone to, I guess this is Gohar's Guides AP Physics 1 review session. My name's Dr. Gold. We're here to get you hyped up and ready for AP Physics 1. What I thought we could do, and I thought would be very helpful, would be to go through the FRQ sections of all the questions. And as we go through, what I'm going to do is, so a lot of these questions, like, I haven't even seen, honestly, but I think that's the best way to teach you guys is to show how my process would be in terms of, you know, attacking a question, strategies I use to get things done quickly and correctly. Rather than if I just know everything and I just go through and speed run it, it's not really gonna teach you anything. So feel free to ask during this whole review session if anything doesn't make any sense. Please just talk about stuff. We'll go through it. And then at the end, yes, I'll take requests for like special topics. So let me get through the FRQs. I'd maybe take like an hour. And then if you have any other like special topic questions, I'll go through those for as much time as I can. I probably got like 3 or 4 hours here. So hang around. We'll have some fun. Yeah, cool. All right, let's do it. All right, let's see. First part here. Let's pull it in. I got that. Cool. Also, let me know if you can't see anything, right? If anything needs to be clear or whatnot, please let me know. Okay. All right. So questions 1, 4, 5, short response, require about 13 minutes each. Cool. 2, 3 require 20. Well, it's nice that they tell you how much time it should require. You know, time management is very good during an exam. I always say, like, keep a watch with you. Okay, cool. All right. Says a cart on a horizontal surface is attached to a spring. The other end of the spring is attached to a wall. The cart is initially held at rest as shown. When the cart is released, the system consisting of the cart and the spring oscillates between the positions plus L and minus L. Cool. So this is what we would call like the equilibrium point, right? Figure 2 shows the kinetic energy of the spark as a function of the system's potential energy. Oh, okay, cool. Nice. Yeah, we love spring problems. Frictional forces are negligible. We love that. Like, no friction. Thank you. On the graph of kinetic energy versus potential energy shown, for the values of the x-intercept and y-intercept are the same. Explain why this is true. Knowing this should be fairly obvious to you guys, right? You know, this is just conservation of energy, right? I always love how, like, yeah, some of the physics questions here for the free response is almost like an English part. Like, there's not really any math going on. But, yeah, this is just conservation of energy. So you can just say that, you know, the total energy must be the same at all points in time. So whenever you're kinetic energy has gone completely down, your potential energy needs to go completely up, and so they all have to like total up to 4. Well, so the FRQ section, there are 2 sections of the exam, Jeff. So this is the part where a lot of it is writing, but there is math. We're gonna do some math here. There's some math. We can do some math right here. We start dropping some stuff. Yeah. Okay, cool. Now things start involving some math. Okay, so when the cart is at plus L and momentarily at rest, a block is dropped onto the cart as shown. The block sticks to the cart, and then the block cart spring continues to oscillate between minus L and L. The masses of the cart are MO and 3MO respectively. The frequency of oscillations before the block is F1. The frequency F2. Calculate the numerical ratio of F2 to F1. This is a good one. Okay. Does anyone remember what the oscillation is? The natural frequency of oscillations is for a spring? Kind of a good one to know. Y'all can type in the chat if you know. I like interaction. So square root of L over G is for pendulums. That's correct. Yeah, this is L over G. This is for pendulums. Because that's length and gravity. M over K. Yeah, it's close. It's square root of K over M is equal to, this is what's like, it's proportional. I think there's a 2 pi in there somewhere, but like whatever. I think this is omega. Yeah. If you want to remember why, guys, yeah, this is also a very important thing to remember, is you want to look at limiting cases. So frequency, right? Let's remember is how fast something oscillates back and forth, right? And that, is related to K, which is the stiffness of the spring, and M, which is the mass that's attached to it. So if your spring gets stiffer, right, if K goes up, then the frequency, like how fast it oscillates, should also go up. So yeah, if you ever forget, you can try to think of like what happens if K goes up. If K goes up, the spring gets stiffer, so this thing should oscillate quicker. M is the mass, right? If the mass on the end of my spring gets smaller, right, then there's less force needed to like move this thing around, so it's going to move around quicker. So that's how I remember it. Yeah, less mass. If you divide by a smaller number, things get bigger, and if there's a bigger number, things get bigger. So that's how I remember that. Okay. So the K stays the same for both when the first mass is on it and when the 4 mass is on it. So we don't really even need this, So we can just say that omega is proportional to 1 over the square root of M, okay? Or you can say this, 1 over the square root of M, okay? So remember that omega 2, right, is 1 over the square root of 4M naught, and omega 1 is equal to 1 over the square root of 1M naught, right? Because omega 1, or here, they want F, but F and omega, it's just a factor of 2 pi. Don't worry about that. But F1 is when there's only 1 M naught mass on it, and then F2 is when you have 4 M naughts on it. So then the ratio of F2 to F1 is going to be 1 over the square root of 4 M naught over 1 over just the square root of M naught, which, if we remember how to divide fractions, right? Flipsies, was it keep, change, flip or something? That's going to become, we're going to have the square root of M naught over the square root of 4 M naught. So that's just going to be equal to 1/2, right? M naught cancels, and you get 1 over 2. Yeah. So yeah, so the frequency is going to decrease by a factor of 2. If something is constant for 2 things, we can just treat it as 1. You can, because when you divide it out here, Dylan, it's just going to cancel, right? In the case here, right, if I had omega 1, right, was equal to square root of K, what was it? K1 over M1. And then we divide that by omega 2, which is square root of K2 over M2. If K1 equals K2, right, when I go to divide, it's the same thing on the top and the bottom. So you can just cross it out. Yeah. So yeah, so numerical value of this is equal to 1/2. And I have the solution, so I can just check like real quick as we're going. Yeah, we're good. All right, cool, awesome. All right, let's roll. Okay, then we got another picture here. A sec. Yes, you're right, Jeff. Also, the total work is the integral of kx dx, which they end up... So again, AP Physics 1 doesn't want you to use as much calculus. It used to be like a very strictly numerical like algebra calculator based course. But you're right. They would just give you the formula, which is energy of a spring is 1/2 kx squared. And yes, for any of those that know calculus, where this comes from is you're integrating from x0 to x1 of kx dx. This is a little preview for like where the calculus comes from. Okay. So quick thing, guys. Don't worry about screenshotting, because I will download the whole whiteboard as a PDF and I'll post it for you guys. Also, all of this is getting recorded to Twitch, so you can go back and rewatch the whole thing. So if you got to dip out, go eat some like nachos or something, bring me some. But you can go back and watch the whole thing. Don't worry, this is all recorded, and I'll dump the PDF for you guys afterwards. Yeah. Yes, and you can set the kinetic energy, Jeff. Yeah. Yeah. I know there's always this thing. I remember, too, when I was a student, being like, oh, man, I have to copy what the professor's doing. I got to write it down, because you feel like obligated that you're not going to learn if you don't copy it down. But focus on, instead of writing things and copying things, focus on, like, learning. That's why it's here. You can always rewatch it if you want to. Don't waste your resources thinking you have to copy things really quickly. Write down notes if things make more sense to you. That's cool. But every little thing, it'll come back in a PDF. You guys are good. Can you link the Twitch? Yeah. Let me show that real quick. Let's see. Twitch. Yeah, this is my. There you go. That's my Twitch. I will dump the PDF in whatever channel I need to, and I'll ping. I'll have whatever the mod is. Like, tell me where. Oh, this is Infinite Dr. Golds, but I'll have whoever the mod is ping the right people. But also, yeah, that's the Twitch channel. If you ever want to watch, the recording immediately, that's where it'll be. I will then get a YouTube link once I transfer it over there, and I'll have whoever the mod is in your server post where that link will be. But you can watch it immediately over there. Yeah. Okay. All right. Okay, the dash line. Okay, for the block card spring, after the block is dropped onto the cart, the graph is identical to the graph shown in Figure 2. For the cart spring system before the cart is dropped to the cart. Okay, whatever. Okay. Explain why the two graphs must be the same using the physics principle. Yeah, I mean, the energy has to be the same because there was no change to this, right? So this actually comes, Jeff, what we're talking about, is that the potential energy was 1/2 kx squared, right? And let's remember that when we dropped the mass onto the other cart, it was still oscillating from negative L to L, okay? So the potential energy is still 1/2 k L squared. Yeah, exactly. Yeah, so this does not change. However, the kinetic energy will not change, but some values in it will. So let's remember that the kinetic energy is 1/2 mv squared. So when this thing has the minimum amount of L, which means it has the maximum amount of V, because now there is more mass, this means that the maximum velocity of the 4-mass system has to be less than the maximum velocity of it just being a 1-mass system. Yeah. Okay, so does that make sense? So the value of the energy, the total energy, is going to stay the same. However, when we look at kinetic energy, the maximum velocity is now going to be less. You don't have to say that here. You just have to say that the reason why the two graphs are the same is because the maximum amplitude of the oscillation does not change. So half the velocity it takes, let's think. Yes, yeah, you're right, Jeff, yeah. Because mass is going up by a factor of 4, which means this needs to go down by a factor of 4. But because it's squared, that means it's going to go, the velocity goes down by a factor of 2. Yeah. This is an important thing also in physics to understand how, like, trends work. They call this like scaling, for instance. You want to say, oh, if this, for instance, if A goes as B squared, right? That means if B doubles, then A quadruples. Or if we say 1 over B, right? You know, as this goes down by 2, this goes down. As this goes down by 2, this goes up by 2, and then like square roots and this useful stuff you'll use outside of physics. It's very useful. Okay. Consider a system that only consists of the cart and the spring. On Figure 4, sketch a solid line that shows the kinetic energy of the system, but not the block after the block is dropped onto the cart. Oh, let's see. Oh, okay. Okay.
Nice.
Cool. Yeah, thanks for following. Let's see. Okay. So, yeah, the issue here is right. Okay. The potential. So when they're talking about like just the cart, right? So let's consider what these values are, right? Potential energy is always 1/2 kx squared. You notice how this does not depend on the mass, right? The potential energy just has a k term and an x term. Are you good at theory of chances? Maybe, Felina. Post an example of it. So when we're looking at our new graph here, let me just, I think I can just screenshot this thing. Let me just screenshot it down so we can write on top of it. Okay. No. There we go. Okay. It is, yeah. Kx is the force, and then, yeah, 1/2 kx squared is the energy. So the potential energy is still going to peak here at 4. So what they're talking about is they're saying that we have, right, the, what was it? We have, like, the m naught, like, of the cart, and then we have this 3m naught that was put on top. And they're asking for just the kinetic and potential graph of this part, okay? So, what happens here, right, is that the potential energy of this system, again, does not depend on the mass. So even if we're just looking at the m naught on the bottom, this is still going to peak here at 4. However, when we're looking at the kinetic energy, right, let's remember that kinetic energy is equal to 1/2 mv squared. This, in total, has to equal 4 for both systems. So I have 1/2 m naught v squared plus 1/2 3m naught v squared has to equal to 4, because this is the kinetic energy of this bottom part of the system, and this is the kinetic energy of this top block part of the system that was dropped on. Okay, but they're saying, what is just the kinetic energy of this bottom part? They just want this. Okay, so what you should notice is, like, what's the ratio of this, right? They're going to have the same velocity because they're attached to each other. However, the bottom block, right, only has 1 m naught, whereas the top block has 3 m naught. So this is going to have 3 times the amount of energy that this does. So if we're looking at the kinetic energy of just the bottom block, it's overall 1/4 of the total energy. So instead of being 4 up here, the kinetic energy of just the bottom block is going to be 1 when the potential energy is 0. Does that make sense why it is, guys? So this is what the graph's going to be here. I'll make a little thick line for it. There we go. That's the thick line. So that would be for the bottom one, for instance. They don't ask for the top one, but if you wanted to know that as well, that would look like this. Okay? And then the important thing, right, is that the energy, the total energy of both the bottom block and the top block always adds up to what the total energy of the system needs to be, which is 4. Will I learn this in AP Physics? Yes, you will learn this in AP Physics. Yeah. Okay, cool. That makes sense? It's kind of a weirder question, but all good. Yes, I'll repeat why it's 1/4. Totally cool. All right. Sure. Okay. So, the total energy of the whole system at any point in time has to be 4 joules, right? Because, as we said before here, the two graphs, they're talking about the situation where you just have a single m naught block moving between minus L and L. And then when you have a 4m naught moving between minus L and L, because you've dropped an additional 3m naught on it. And what we said is that the graph of the total energy has to be the same, because the potential energy, right, which is 1/2 kx squared, does not change. It does not depend on the mass. So you're still going to have a maximum of 4 joules of potential energy when your kinetic is down. But then when your potential goes all the way down to here, your kinetic has to also still be 4, because the total has to be 4. But what they're doing in part 2 is they're saying, let's look at just the kinetic energy of the bottom part of the 4m0 system, which is just the 1m0, like the smaller block. And what we said here is that, okay, well, if we look at the equation for kinetic energy, that's 1/2 mv squared. Thanks, Hell Dog. That's 1/2 mv squared. And the kinetic energy of the whole system, which is the 3m0 and the 1m0, has to equal to 4 here when the potential energy of the whole system is 0. The potential energy of the whole system is 0 when it gets to this point, right? Because this is where, when we do like 1/2 kx squared, this is where x is 0. When the block is, so the block moves, right, between like, can I move my block? Well, 1 second. All right. Here, I want a solid block. Where's my solid block? There we go. I like that. There we go. So when this block moves between here and here, right, this is the point, right, where it has the maximum potential energy and no kinetic energy. This is the point where it has no potential energy but maximum kinetic energy, and then vice versa, right? This is, again, maximum potential, no kinetic. What tool am I using for this? Oh, it's just a whiteboard tool I have. I've been using it for years. It's called Group World, is what it is. But yeah, they're great. I've been using them for a while. So what happens is when we get to this point, right, where there is no potential energy and there's maximum kinetic energy, we still need to have 4 joules of total energy. Because from our graph here, right, the total energy needs to always remain the same. So when the potential energy goes down to 0, I still need to have 4 joules of total energy, all right? Now, that 4 joules of total energy comes strictly from kinetic because there is no potential. And the kinetic energy is split between the 3 mass on the top and the 1 mass on the bottom. They're connected to each other. And that's 1/2 mv squared. So what we're going to have is the 1/2 mv squared of the bottom block plus the 1/2 mv squared of the top block has to be equal to 4. Okay? Does that make sense so far? Die for us? Is that or whatever you want me to call you? That makes sense? Okay, cool. So if I look at how this is split, like how this is divided, yeah, total mechanical energy in the system is conserved. Yeah, as long as there's no friction or like outside stuff happening, you're okay. So what happens here is because, let's look at the ratios of this, right? Look, they both have a 1/2. They both have a v squared. The v squared is the same because the velocities are the same because they're both moving together. But if we look at this mass term, do you see how this has a 1m, but this has a 3m? Okay. So that means the ratio of the kinetic energies on both sides, right? This is like 1 to 3. This is going to be 3 times this. And so okay. If this energy has to be 3 times this energy, but I need both energies to add up to 4, right? The ratios are kind of already there for you, which is nice. Then you know this is 1 joule, this is 3 joules, because if we add them up, we get 4, and the ratios of them is also still 3 to 1, which is nice. If they had not put 4 here, let's say, for instance, they had put, like, let's say this graph was different. Let's say the total energy was 6, right? Then what you need is you need some ratio of 1 to 3 that still adds up to 6. So a way to solve this algebraically, right, would be that, like, 1x plus 3x has to be equal to 6, right? Because this is the ratio of 1 to 3. So you can solve for this, right? This is 4x is equal to 6. So you get x is equal to 3/2. So now if you wanted to solve for what the energies would be, right, this total energy would be 3/2 of a joule, and this total energy would be 9/2 of a joule. And that would add up to your 6 joules total. They gave you a little bit of a softball here because they made the ratio 1 to 3, the mass ratio 1 to 3, and they also made the total energy 4. They were nice to you, which is, you know, sometimes AP Physics is nice to you. Yeah, thanks, Jeff. Yeah, you're good. Yeah, we're doing physics today. That makes sense? Cool. All right, good. Yeah, awesome. Yeah, again, if anything doesn't make sense, please, you know, raise your hand or ask a question. You know, that's the best way to learn. I don't want you to just nod your head and be like, Like, that's what happens all the time in your classes. I understand that. All right, let me clean some of this up for the PDF later. Yeah, we don't need this example. Yeah, let's get rid of this. Okay, cool. All right, awesome. All right, let's go. Yeah, real. Okay, students conduct an experiment to determine the acceleration of a cart down a ramp. Ooh, we love inclined planes. The cart is released from rest at the top of ramp at t equals 0 and moves down the ramp. The x-axis is defined parallel to the ramp. That's cool. All right, so they're defining the x-axis in this direction. Collect the data in the following table. Indicate what quantities could be graphed to yield a straight line whose slope could be used to determine the acceleration of the cart. You may be asked to use the remaining columns in the table as needed to record any quantities, including units not already in the table. Okay. Let's see. Okay, so we got position. We got time. Oh, okay. So, let's... When they want to, like, graph stuff and come up with trends, and notice how they say a straight line, right? That means we want to graph something versus something, and then the slope will be what... So the classic example of this is a spring. Let's say, for instance, you wanted to graph the force versus the displacement, right? Because you know force is equal to k, or negative kx is what it is. But let's just pretend it's just positive. Okay? If you were then to graph some sort of line... Notice how this also looks like, for instance, y equals to mx plus b, where the slope, m, right, in this case, would be k. This is a very common... We do this in physics. You'll do this also if you end up doing grad school or any sort of, research. It's all about graphing something versus something and then seeing whether it's a straight line and then the slope of that straight line indicates it's one of the quantities you're trying to solve for. This is a really cool concept. We do this all the time in physics. But in this case, we're trying to find the acceleration, okay? So, I need to know something that relates position and time and acceleration. This is where we start thinking back to our kinematics equations, right? Which here, let me pull up the equation sheet they're going to give you, because that'll probably help us the best here. Let's see. Because I know some people use SUVAT, some people use other ones. Oh, I see. They use VX naught. Okay, cool. That's good. I like that. Okay. So if we look at our equation sheet, right, I need something that relates position and time. And so looking straight away at the top equations here, this has velocities and times. I don't really want that, right? I don't see any velocities here, so we're not gonna use that one. It means I'm not gonna use this one either. Okay. So yeah, good. The second one, yes. Let's use the second one. The second one makes the most sense here, right? So we have position, right? Initial velocity. I think this thing is dropped at rest. Yeah, so released from rest, guys. Anytime you see that, that just means V naught is just 0. So we don't use that. So we literally just have this. So we have x is equal to x naught plus 1/2 at squared. And the other cool thing, right, is that x naught was well, okay, no, they call this 0. Okay, that's fine. Okay. Yeah, it's just this. Okay, cool. So it's just this. X is equal to 1/2 at squared. Yeah, vt plus 1/2 at squared. But Felix, that vt is the initial velocity, which is 0. So if I wanted to figure out what the acceleration was, right? Let's remember, I want something in this form. I want something in like y is equal to mx plus b, where I want the thing I'm solving for to be the slope, okay? So in this case, this kind of looks like, right? X is equal to, what is this going to be like? A is 1/2 A. Or let's use different colors for this. I want to use this. T squared here. And then, here, let me move that. Yeah. Okay. I have some students that say they have like synesthesia, but with like numbers. They can see numbers as colors. I think it's like super cool. But okay. All right. Yeah. So this is, and then here, this one will right here is kind of like B. So again, this would be the equation of a line, right? Y is equal to mx plus b, right? And this is graphing y versus x. In this case, right, the slope is going to be 1/2 a. I'm trying to solve for a, right, the acceleration. But I'm going to be graphing x versus t squared, okay? I know that sounds counterintuitive, right? So So you don't I know you don't want to put x on this axis usually. You're just like, I don't like that, but you have to at this point. So you're going to graph x versus t squared, okay? And if you graph x versus t squared, right, which is the same thing as graphing y versus x, then the slope of whatever this line is, the slope here, is going to be 1/2 a. Yeah, constants are always grouped with the slope. Yes, they are. They are. Yeah, they're not included here. Yeah, no. I mean, you could, if you wanted to graph this versus like 1/2 t squared, you could. Like, you could take this and make this like, you could say this is like 1/2 t squared, right? And then the slope would strictly be a. But that's not conventional. We don't usually do that. So I think what you would want to say is you'd want to say t squared. Why, Lightning says? Why what? Why what? It's okay. What's up? Tell me what doesn't make sense. I'll explain things as many times as we need to. Oh, why would I put the 1/2 in front of the t squared? Again, you don't really have to. You could graph this as versus 1/2 t squared, but I think for the answer, let's see on the solutions. Let's see what they do. I'm curious. Okay, they just do t squared. Very interesting. Okay. You're right that you could graph it versus 1/2 t squared, and then the slope strictly would be a. So here, this is the solution they put for it. I agree. No, you're okay, Lightning. We could say that it was also equal to 1/2 t squared, and then this would actually be the acceleration. If you're graphing this versus t squared, right? The issue is this slope that you get when you do this versus this is going to be 1/2 a. So you have to end up multiplying it by 2 to get the actual acceleration. Couldn't you find the velocity by using v equals x over t and then plot velocity versus time? No, because the velocity is changing. Yeah. The problem is, like, velocity is equal to change in position over change in time, right? And so then you need to graph the change in velocity. So it requires, like, 2 sets of graphs. You don't want to do that. That's just, like, too much. You could compute dv dt. You could, although you don't really have as many data points here. So, anyways. Vertical axis, I would put position. Horizontal axis, you could say 1/2 t squared. They want you to just say t squared. That's kind of, I don't think you'd get points off if you said 1/2 t squared. They just want you to do that. What's up, BB? Good to see you, dude. Oh, so it says, why can't we do a velocity time graph? Okay. Okay. Reason why is they say they want quantities could be graphed to yield a straight line whose slope could be used to determine the acceleration of the cart. Okay. So if we did, for instance, yeah, it's okay. I mean, let's see what would happen, right? If we did this versus time, yeah, okay. You would have to do the difference in position, right? This would be delta x, and then you would have to divide it by this delta t, and that would yield you a v, right? But then remember, acceleration is equal to change in v over change in t. So if you were to calculate the change in position versus the change in time, which is the velocity, for each one of these time steps, okay, that would give you a velocity between each time step. And that velocity is changing, by the way. And then you would need to graph that velocity versus time in order. So then you would have to graph the change in that velocity versus time. It is possible, yeah, but it's way too lengthy. Yeah, you have to end up doing two sets of graphs or 2 sets of you have to keep calculating deltas like twice. The better strat when you see this is they want a very simple answer, which they just want a simple y equals mx plus b type of thing. So this is the easiest way to do it. You're correct. You could do what you're doing, but it just wouldn't like work out too much. Yeah, Nolan. Yeah, Philip and I've seen Patty. I haven't seen Philip. I've seen Patty. I've seen Patty before. Okay. All right. So that makes sense so far. Okay. Cool. And then they say create a graph. Well, I don't know. This is kind of silly. I may just post the solutions for this one because I don't really want to go through and waste your time like doing calculator stuff. Yeah, it's just a sketch, right? Yeah. Well, okay, so what you would need to do then, guys, is so first of all, you have to know that you have to graph t squared, right? Which means now you need to calculate what t squared is for each one of these time points. Yes, exactly. Yep. So, I mean, if you pulled up, the calculator here, this is just as simple as saying like 0.39 squared, right? And look how that gets you 0.15, and so that's what they put for here. They calculate that for each time point. If x sub 0 was a greater value than 1, b would be the constant, correct? Yes. So if, for instance, this thing did not start at 0, let's say the cart started like right here or something, then you're super correct. There would be an offset. That would be the y-intercept. And that's another important thing. When in graphing in physics, a lot of times, sometimes the slope is one quantity, right? And then this would be the other quantity. The intercept becomes something else. Yeah. That calculator, where can I purchase it? It doesn't exist. I just reskinned. I reskinned a TI-84 emulator. It's fun. I can show you guys how to do that at some point, but yeah, cool. Also about the delta VT graph, isn't the velocity instantaneous kind of graph? It would give you average velocity. Yeah, exactly. It would give you average velocity. So anyways, you would have this and whatever, you graph it, cool, you're going to find a slope. And yeah, so when you get your slope, if you're graphing x versus t squared, remember that the thing was x was equal to 1/2 at squared. So whatever this slope is that you get is equal to 1/2 a. So the acceleration is going to be equal to 2 times the slope. This is the important thing you have to do. I'll just grab their sketch. Where'd my mouse go? There's my mouse. Real soon, not right. Oh man. Okay, here. Let's just grab their graph so I can kind of show you how it works. All right. Okay, so this is if you graph the position versus the time squared, you get this. They want you to calculate a slope. It's kind of messy. There's no real nice intersection points. I'd maybe say this one. What are they doing here? This is like, I want something that like nothing hits. Oh, this does. Ooh, we like this. This is good. Yes. So when time is equal to 1, position is equal to 4. So if you wanted to calculate the slope, right, that's going to be y2 minus y1. So it's 0.4 minus 0 over x2 minus x1, right? So that's just the slope is equal to 0.4. And then we multiply that by 2, right? So 0.4 times 2. So that's going to get us at 0.8 meters per second squared. Should be the acceleration. Yes, you would need to specify that. Yeah, you need to show that like the slope is this, but in order to get the acceleration, that because it's 1/2 at squared, that yeah, it needs to be that. Helldog says, are there better iterations of the TI-89? The 89 is, in my opinion, the best calculator. I do not like the Inspires and stuff. Once they started putting like GUIs and stuff on it, I was like, stop. It was just kind of nuts. Interesting, yeah. Yeah. Okay. Cool. And yeah, they get the same thing. They get like 0.8 meters per second squared. Cool. All right, that works out. Nice. Okay. Oh. Here we go. 1 sec. This is part B. Let's see. They said the students were asked to determine using what additional quantities do they need in order to measure G experimental. I think that's just what we just needed the slope. That's all we said it was, right? Oh, to calculate G. Oh, sorry. Oh, this is calculating. Oh, this is cool. Okay. I just love how everything is gold. Yeah. Yeah, I have a kind of a theme going on. That's why I'm Dr. Gold. That's where it comes from. Yeah. Oh, I also this is kind of here. I'll show you guys. I have I make shirts sometimes. This is like a fun little shirt I make. Little Nike logo. But But okay, so they want to say, like, could we determine what the experimental value for gravity is from this acceleration? And we could, right? Because if we remember from an inclined plane, right? If we have a block here, right? You have the force of gravity pulling it down. You're going to have the normal force pointing straight up. And I think we assumed there was not really as much friction, right? So, let's see. There we go. There's that. There's that. Let's remember, right, that if this is theta, this is also theta. If you guys ever need to remember why this is, remember that if this angle, right, were to decrease, I call this like the limiting cases thing. If this angle were to go down, then the angle between gravity and like the normal, the anti-normal to it would also go down. So that's how I remember like which theta corresponds to which theta. I just look at like if this thing goes down, does this thing go down? Yes, cool. They're the same theta. But remember that this would be right. This would be FG sine theta, would be this side, and then this would be FG cosine theta. Okay, and then FG is equal to mg, right? So if we know that something has an acceleration going in this direction, let's remember from, right, sum of forces in, let's say, the x direction has to equal the mass times the acceleration in the x direction, which is just a. That's just going to be equal to FG sine theta, which is just equal to mg sine theta. So what this question is asking is, what else would I need in order to calculate g, right? And so if we had done the classic pulley problem or something, oh, you don't get, okay, that's totally cool. Let's go over that. Okay, so this makes a triangle, right, guys? So mg points straight down. Here, let me take this and like blow it out over here. Okay. Let's remember that this is theta, right? And then this is mg. The force of gravity, which in this case is the hypotenuse of my triangle, is mg. That points straight down. Then this component, let's remember that sine of theta, right, is equal to the opposite over the hypotenuse, right? So we're going to call this fx, because this is the amount of force that is pointing in the x direction. So that's going to be fx over the hypotenuse, which is just mg. So if you move this to the other side, you get that mg sine theta is equal to fx. Because sine brings you down, but sin brings you down. That's a cute way to remember it. I like that. That's fun. Yeah, you don't really need m. Actually, you don't. Yeah, you don't. And we'll show why, right? So some of the forces, which is mass times acceleration, right? And there's only one force. There's only one force in the x direction, and it's the force of gravity pulling it in the x direction. Okay. So the mass actually cancels out here, which is nice. So this is going to go away. This is going to go away, and you end up just getting ax, right? Which is just a. It's the only a we're looking at, is equal to g sine theta. So if I could determine a from my experimental results, right, in what we did here, right, we determined a from the slope of measuring the position versus the time squared. Then I could determine a value for what g should be if I knew what theta was. Does that make sense? Yeah. So they're saying, again, it is kind of tricky. It tripped me up at first. I was like, wait, g? Like, what? We already know what g is. We know what g should be theoretically. We know that g should be equal to 9.81 or 10 if your teacher's lazy. But that's what we notice theoretically. But you can do experiments to see experimentally what you get from that value. No, you don't need to take the inverse sine. Because what you would need here is you would need theta. In order to get what g is, that's just going to be a divided by the sine of theta. You would need to measure. So this is what they're asking. They're saying, what additional quantities do I need, like from my experiment, in order to get g? Well, in order to get g, I need the sine of theta. And so I just need to know theta for what this is. And then they say write an expression for it, and like, cool, we just did it. It's a over sine theta. That's what this is. Yeah, that's a weird question, honestly. For them to jump to this all of a sudden is like, I don't know. I'm not the hugest fan of that. that make sense to you guys? I'll take a little 20 second break. Y'all can catch up. Yeah, several people are typing. Cool. What is experimental? Yeah, this is cool. So, because for instance, when I went to grad school, you get two choices. You either now you get three, but you either become a theoretical physicist or you become an experimental physicist. Now there's what's called computational physicist because of all the AI stuff and the computer things, and that's where like you kind of blend between the two. So experimental means like going out to the real world, testing things, doing things, measuring things, you know, with, I don't know, a ruler or in my case, like an oscilloscope, and trying to determine what values of things should be. So for instance, this is an experimental way to determine what G is, right? The constant for the acceleration due to gravity. Theoretical is not doing anything in the real world, but like just strictly using pen and paper and equations to derive what the value of G should be. Yeah. So experimental value is going out measuring things in the real world. That's what you're doing here. Whoever was doing this experiment was literally taking a cart, running it down an inclined plane. They were measuring the position. They were measuring the time squared. And then from that, they were like, cool. Theoretically, G should be equal to the acceleration over sine theta. And this value was determined experimentally. It's kind of, it's a cool blend between the two. And this is also what you do in grad school as an experimentalist is you measure something and then you ask your theorist friend, hey man, does this make sense? Like, should it be this? Like, what should it be? And then you can verify. Specific order. I'm just going front to back on the questions. Let me see if there's a rotational question next. There is. The next question is rotational. So stay tuned. Yeah. This one's almost done. We're on part B. Yes, exactly. Yes. Wait, would they ask us to find the experimental steps? They would. And sometimes they kind of did here, honestly, right? They ask you, like, what would you need to measure, right? What would I need to record? I've seen questions where they say, describe how you would do this or what tools you would need. And that's when you have to say, like, oh, I need a ruler to measure this. I'd need a scale to measure this. They do ask those questions sometimes. Fembox. What's up, Fembox? Yeah, physics. Okay. All right. Let's go to the next part. Okay, they say, bro is teaching me in 5 minutes, which is my 3 days of yap. Doubles understands. Yeah, it's cool. If you guys also want, like, again, like, quick stuff in physics, I don't know if you like TikTok or YouTube, but I run a TikTok channel as well where I make, like, quick little tutorial videos. So if you need help with, like, Lewis structures, I try to do stuff in, like, a minute is what I do for some, but some of the stuff takes, like, 3 minutes. So if you have questions about, like, centripetal circular motion and stuff, I do cute little TikTok videos there. I try to explain stuff really quickly. So there you go. Yeah, calculus, whatever. A bunch of math stuff. You guys can go check that out at some point. Just free resources for you guys. Yeah. Anyways, all right. So it says the students calculate G experimental to be significantly lower. So this is always the problem with experimental physics is that sometimes, a lot of times, there's error due to things such as friction or, I don't know, just not writing down the right numbers, numerical stuff, and you won't get values that that you were supposed to get. Okay. So here it says the value of G is the students calculate the value of G to be significantly lower than the accepted value. All right. So let's remember that G was equal to A over sine theta. Okay. So G was equal to A over sine theta, right? And they're saying, oh, the G I calculate is a lot lower than the 9.8 it was supposed to be. Yeah, the VODs are saved, Rio. You can see them. And then also the mods will they'll post it on YouTube. I will post it on YouTube and they will post the link for you guys. Okay, so if this is if the value of G we calculated is much lower, that means the acceleration that we measured is lower than it should have been. So this is where we should think, okay, what would cause the cart to not go down and accelerate as much as it should have, right? And they say, what is a physical reason other than friction? Oh, they don't let us say that? Man, these are the most obvious ones, dog, but that's mean. That's super mean. That could lead to significant difference. Okay. Well, I would say friction or air resistance. That's what it should be. Oh, man. You could say the wrong angle was measured, I guess. If they won't let us talk about this, we could say that the wrong angle was measured, I guess. Let me see what they put down. Oh, okay, they do, yeah. I know, that is crazy obvious, but they don't let us use that. Let's look at the scoring for this. I always love watching what their scoring is. Okay, they say except one of the following. A physical factor in the materials used, e.g. the wheels have non-negligible rotational inertia. The ramp was bumpy. The wheels were wobbly. Okay, but this is what I said. I said a physical error in the measurement collection. Yeah, if the wrong angle was measured, that would change it. In reality, they should have let you say that this is the error, because that is really what's going to happen is friction. That's what they say statement of human error does not earn a point. Yeah, does not. Because this is too general. To just say human error causes something, yes, it does, but it's too general of an answer. I think specifically they're talking about what would lead, because this is actually the next part. They're saying what would lead to a decrease in the value, right? Error in calculation does, but they don't say that, right? I don't think they say that, because they say measurement collection. You have to be specific enough. If you're talking about your human error, you have to be like, what part of the human error? In this case, it's the measurement collection, and this is cool. So if I need this value of G I calculate to be lower than it should be, okay, that means I would need sine theta to be bigger, okay, which means this would lead to a decrease if the measured angle was too high. This is the important part. You can say, cool, the angle will affect it, but now you have to say whether you overestimated or underestimated theta would lead to that difference. Because if you underestimated theta, that would lead to an increased value of G experimental. Because if this goes down, then this goes up. They want to specifically know what did you do wrong so that G goes down. G goes down if you measure a theta that's too big, because you're dividing by a bigger number. I would have said the experiment's being done on a different planet. I mean, maybe. I mean, they kind of say that, actually. Look at this. They say a physical factor in the environment, the room was being accelerated. What type of room is being accelerated? Excuse me. Oh, okay, in the elevator. Okay, I guess you could do it in the elevator, sure. Yeah, I guess that does count. It's not really a room. Or high elevation or on a different planet. Yeah, you could have said this. Okay, you could have said it. Correct. Yeah, sine goes up with angle. It does for low angles. It does, right? Once you start going on the other side, it starts going back down. So as the denominator goes up, number goes down. Correctly. Yeah, exactly. So in order to calculate a G that is too low, sine of theta would need to go up. You'd have to measure an angle that's too high. Let's see if they say that. Do they say that? Oh, they just say the functional dependence of it. That's all they say. Okay. Yeah, does that make sense? Yeah? That's kind of a weird question, honestly. I don't really like that one. Okay, now they're talking about, like, up the ramp. Okay. Last part of this, then we're going to go to rotation stuff. I know, everyone always gets messed up on rotation. Okay, students want to confirm the acceleration is the same whether it rolls up or down. The students start the car at the bottom, give the car a quick push, so it rolls up the ramp and momentarily comes to rest. Okay, cool. On the scenario, sketch the X position versus velocity as a function of time that correspond. Okay, cool. All right. So, I usually like to graph the velocity first, and then from that I can kind of graph the position. You hate rotation? What's wrong with rotation? I hate it. So this is what I'm teaching later this afternoon for AP Physics 2. I hate optics. I really don't like optics. It's just a bunch of like memorizing like which way does it go. Yeah, rotation for life, dude. Oh. Okay. So you have to always like consider what the coordinate system is. They're calling this is x is equal to 0 and this is positive x, right? So if this car is moving up the ramp, right? The velocity will be negative because the change in x over change in time is getting less. It's negative, right? We're going from like, let's say x is equal to 50 to like x is equal to 2. See how like delta x is changing? Oh, nice. You got a 5. Good job, dude. Yeah. So when looking at the velocity here, it's going to start with some big negative value. And then eventually, when it comes to rest, that means the velocity needs to be 0. So it's going to do something like this. Okay? So once I have this, now I can kind of like graph like what the position is. This is where I like to use like the happy face, sad face, like neutral face. The position, when it starts, right, at time equals 0, is going to be something far away and positive. That's going to be here, right? And then, let's say it comes to a stop somewhere up here. So that means the x position is going to be less. So that's going to be somewhere here. When graphing position graphs from velocity graphs, you have 3 decisions. You can either draw what I call like a sad face, right? That looks like this. You can draw a happy face, which looks like this. Right? This is called concave up. Or you can just draw a straight line between them. Okay? And the concavity, right, which way it's curved, like curved up, down, or straight, depends on the acceleration. And the acceleration, right, let's remember, is the slope of the velocity graph. Okay? The slope of this, right, slope is positive. Okay? Because this is going up. And so if the slope is positive, this means your graph needs to be concave up. Okay? So concave up means it needs to be happy. That's what I said. It's like happy face. We like that. So going from here to here, I need something that's concave up. So that's going to look something like this. The happy part of it is like if I were to like keep doing, you know, it would be something like that. But in reality, it just keeps going straight. Yeah. In physics 1, change in acceleration is always constant. Yes. Change in acceleration is called jerk. And then there's actually a couple other ones. Let me see. We snap. Do you guys know this? Like physicists come up with all sorts of funny stuff. Wait, no, that's not that. What is it? Jerk, acceleration. One sec. There's a whole thing for it. This is it. Yeah. So, one second. Let me show you. Yeah. So, right, you have position. Velocity is the derivative of position. Acceleration is the derivative of velocity. Jerk is the derivative of acceleration. Snap is the derivative of jerk. Crackle. Yeah, I don't know. Physicists are funny. They come up with some funny things sometimes. It's pretty hilarious. They do this also with like the quarks. They'll say like top down beauty something. Yeah, they're funny. What are you studying, son? Jerk. But okay, that's how this goes. I think that's it for this question. Yeah, does that make sense, everyone? I'll take like 10 seconds before I move on to the next one. Yeah, you're not going to get an equation on jerk. They're not going to do anything on jerk. That would suck. We don't have to go from velocity to position. You don't have to. You could have graphed this straight off the bat, but I think sometimes, you know, it's hard as a student to know intuitively which, like, whether it's this way or this way. So I like to graph the velocity first. I know the velocity starts off as like very negative, and the velocity eventually goes to 0 when it stops. And like once I have this, then I know, you know, if velocity is this way, then position is this way. If velocity is this way, then position is this way. And then if velocity is this way, then position is just either this or this. Yeah. It is. It is like AB Calc. Yep. Yep. Yeah, Physics C is all calculus, correct. Yeah. Physics 1 is just, you know, it's funny. They used to call this AP Physics B. Back in the day, they called it B, but then they renamed it to 1 and 2. All right, let's see. Let's pull up another one. No, I like AP Physics C, honestly, because, yeah, equity. Yeah, this is the stream for Gohars. What equations? Oh, you wanted the snap, crackle, pop? Just Google it, like snap, crackle, pop, Helldog. It's there, dude. Yeah. Here, I'll pull it up for you. It was this one. There, I'll send it to you in the. Yeah, there you go. I got you. There's a link. Okay. Okay, let's see. All right. Ooh, look, we got rotational motion and there's a spring involved. Uh-oh. Things about to get tricky. Let's see. Okay, a small block of M naught is attached to the end of a spring of constant K naught that is attached to a rod on horizontal. The rod is attached to a motor so that the rod can rotate at various speeds shown as axis. When the rod is not rotating, the block is at rest and the spring is at an unstretched length L. We like that. All frictional forces are negligible. Yay. I love no friction. Okay. At time t equals t1, the rod is spinning such that the block moves in a circular path with a constant tangential speed, and the spring is stretched a distance d1 from its unstretched length. At time t equals t2, the rod is spinning such that it moves at a speed v2, and it's a distance d2, as shown in the figure. Okay. Where's the question? Okay, here's the question I want. Where can you find these questions? They're on College Board. Just look up College Board. I'll post them as well. I'll post them for you guys. Yeah, it's just look up College Board FRQ 2023 AP Physics 1. They have them. They have all the previous and they have all the solutions. Like, this is a great way to self-study. I mean, I'm happy to do a walkthrough because I feel like I'll teach things along the way that makes sense, but yeah. Okay, on the following dots, represent the blocks and draw the force that exerted on the blocks by the spring at times T1 and T2. The spring force must be represented by distinct arrows. Okay, blah, 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 blah. Draw the relative lengths of the vectors to reflect the magnitudes. Okay, very cool. All right. So let's look at something rotating around in a circle, okay? When something is going around in a circular path like this, all right? And let's say it's going at a constant speed, right? So let's say it's always going at, like, 10 meters per second or whatever, right? The velocity, however, is changing because the direction is changing, right? So if I look at the velocity of the thing right here, you see how the velocity is pointing that way? And then if the thing is here, the velocity is pointing this way. And if here, the velocity is pointing this way, right? So the direction is changing. So even though this thing moves at a constant tangential speed, right? A constant speed going around, let's say, like, I don't know, 5 meters per second. Because the direction is changing and velocity is a vector, which depends on the magnitude and the direction, this means that there is a change in velocity. And then because there is a change in velocity, there must be an acceleration, okay? So, and that acceleration, right, let's think. If it's changing direction from here to here, right, what happened was the velocity was changing in this direction. It went from going to the right to going up, so it moved that way. And this way it goes from up to the left, so the acceleration, the change in velocity is that way. And this is why acceleration always points towards the center. And what we learn in physics is that this acceleration, okay, is always equal to v squared over r, okay? So where v is the velocity, okay? And so I'd never like to use the term like centripetal force, like it's not real. Like, don't worry about that. There's always what's called like a restoring force. There's some force that provides this acceleration to keep the thing on the circular path. In the case of the spring here, the restoring force is the force of the spring, right? The spring is what keeps this accelerating inwards, right? Because remember, force is equal to mass times acceleration. So if there's an acceleration, right, pulling it in, then there has to be a force pulling it in. In the case of this, it's a spring. It could be a rope. It could be tension. In the case of the roller coaster, right? You guys probably seen this, right? When the roller coaster is like moving around, it's the normal force that provides the force to keep this thing moving around in a circle. Those are the big ones they're going to do for you. So it's either normal force or it's some sort of tension. In this case, the tension is a spring. Yeah, Kx, yeah, we're going to get to it. We're going to get to that. Okay. Yeah. So, I mean, let's just see, right? So let's remember that, right? Forces, do they want all the forces? They want gravity and shit too? Oh no, they just want the force of the spring. Okay. So yes. So let's remember that force is equal to mass times acceleration, right? Or sum of forces. Which in this case, the acceleration of something moving around in a circle is v squared over r. So this is going to have to equal mv squared over r. If we replaced acceleration with v squared over r. Good. Now, because, right, the only force acting on this object, right, the only force really that could keep this thing moving around in a circle is the spring, right? That's the only thing that's pulling it back in. So this also has to be equal to kx. Yeah, I'll go through other questions after. Let's run through the FRQs. We're close. We're like maybe halfway, 2/3. But yeah, I'll have some time to just answer whatever questions afterwards. Yes. So we see here, right, that the force is proportional to the velocity. So if something is spinning around more in a circle, then the force needs to go up. Where this is actually kind of interesting is, yes, the velocity is going up, right? As we get to like T2 here, right? You see how it says at T2 the speed is more. Or let me see, one sec. Well, they don't tell us that, but you can assume it is, right? Because it's stretching out more. If it's stretching out more, right? Remember, like, this is the stretch, right? If this is stretching out more, you need the velocity to go up. And also when it stretches out more, the radius, this is actually kind of a tricky question. The radius of its path, right, is also going to change. So this is interesting. So as the thing moves faster, it's also going to stretch out more, which is also going to kind of like fight its desire to move out more. Or it's going to fight like with the forces. We'll see this, but in general, right? Force is equal to kx, just straight off the bat, and because this is bigger than this means that the force needs to be bigger. So if we were to draw our forces, right, on the first block, it's only going to be this. On the second block, it's going to be something like this. It's going to be something bigger. Yeah. Cool. I'll show you. It's going to get a little trickier because like both things are changing. All right, let's see. All right, then we got this. Referencing D1 and D2, describe your reasoning for drawing the arrows in the length that you did. I would just say that like F is equal to KX, which is equal to K, and then this is going to be L plus D, right? And D2 is greater than D1, so F2 is greater than F1. Okay. Okay. So then they say it's the okay, this is the next part. Yes, it is. It is. Yeah, watch. It's kind of interesting. Oh, why is it getting bigger? Okay. Well, okay. Sorry. Well, they told us, is what they said, right? So look here. They say that D2 is bigger than D1, right? So it's being stretched more. If it's being stretched more, right, the force from the spring is going to be more. Because again, just think about the block. Like, what is acting on the block? It's literally just the spring force. There's nothing else. I mean, there's gravity up and down and normal force, whatever, but they're talking about like the left-right forces. There's only the force of the spring. So because this is bigger than this, right, and the force is kx, which is just proportional to the distance, if the distance this thing is stretched is bigger, then the force must be bigger. Right? Does that make sense? Yes, if it was it wouldn't be negative, it would just be less. So the thing with less stretch has less force. The force does not change directions. Yeah, it is a little confusing, Diefers, because like if we look at, right, again this, right, force, mass times acceleration, you have mv squared of r is equal to kx. These two are kind of related. So watch. So we have mv squared over r is equal to kx, right? And then let's sub in what the values for these are, right? So x was technically equal to, so x is the, or sorry, it's not L plus D, sorry. L is the, no, okay. This, all right, sorry. L is the equilibrium length. So this is wrong. This shouldn't be this. Sorry. Remember when we do F is equal to kx? This is technically like delta x. It's the change in the stretchiness from where the equilibrium point is. Correct. Yeah. So it's just this. It's KD. That's what it is. Oh, negative kx? It is negative. Yeah, okay, yes. Correct. You are correct that it is negative. the issue, and this is the thing in physics, like, I know the minus signs, don't get so hung up on, like, strictly mathematically, like, whether it's positive. It is always negative kx. That negative just means it opposes the way it's getting stretched. So technically, D1 here is negative, right? Because it's being stretched in the negative x direction. So negative kx pushes it back to the right. Oh, I'm frozen? Am I? Let me know. Looks okay on Twitch. Oh, I'm good? Okay, cool. Thanks. Yeah, you are right. Yeah, so f is equal to negative kx. That's correct. But the negative just means it opposes which way it's being stretched. In this case, x is negative. So f being negative k, negative x, these cancel, and that's why you get a positive force to the right. If you want to get, like, specific with the math. But in terms of, like, springs and stuff, don't just blanket memorize it's negative kx. You can just say it's kx, and you have to be, you got to use your intuition to be like, wait a minute, which way is this pointing? Because that will change based on what your convention is. Will there be an AP Physics C review? There was one earlier this week. I think someone else ran it. One of the mods, if you could link it to him. Yeah, there was. I applied for it, but someone else ran it, so it's okay. I'll show you guys. I do have some AP Physics C resources you can use. Because I did I do an AP Physics C review? No, I didn't, but I have a course for it. Yeah. No, it's okay. All right. Everything makes sense so far? So when K's, yeah, I'm going to show you why. I'm going to show you why that is, Pump. That's a good point. Very good point. So, okay, let's remember. Sum of forces Kx, right, is equal to mv squared over r. So this is just going to be K times d, right? Was d the distance? Yeah, d's the distance. Yeah, K is the distance. Okay, but here's the cool thing. The radius is also changing, right? The radius, let's remember, right, is L plus D. What's up, Misty? I'm doing a physics review, Mystic. Some physics review for some kids on Gohar server. Yeah, this is D. This is going to be D plus L, technically. Okay. Okay. So yeah, watch what happens here. Okay. So if we solve for velocity, right? Does this make sense? Why is it L plus D? Okay, good. All right. Because it's mv squared over r. R is the distance from the center of the rotation to the outside of the rotation. So in this case, when this thing is spinning around, right? R is this whole thing. This is R. Does that make sense, Felix? All right, cool. And R, remember, is L plus D. Or D plus L, whatever. And let's remember that the force, right, is K times D. Yeah? So, if I want to solve for the velocity, right, let's just solve for velocity, right? I get v squared, we move this over, is equal to K times D plus L all over M. Okay? So this is kind of a cool thing we can see, right? So as D goes up, right? This also goes up, okay? And so the velocity goes up like by a factor of D squared plus DL. It's actually interesting. If we were like to multiply this through, this would be K, and then this would be D squared plus DL over M. So V squared goes as D squared, but also an additional DL term. I don't think you need to know this. Wait, for the X and KX, why is it just D again? Because X just refers to the change in the stretchiness of the spring from its equilibrium position. Its equilibrium position, that's when it's like considered not stretched, was just L. The amount it stretches is D. Yeah? Okay. I know this is a good question because like they're combining rotation with springs. It's like a massive like, oh no, what's happening? They like to do this in physics though. They like to combine multiple concepts into one. Yeah. Anyways, okay. So velocity, right? If D goes up, velocity is also going to go up. Does that make sense so far? Why we're saying that? The two worst units together? Yeah, I guess so. Okay. So, if D2 is bigger, then V2 is gonna be bigger. So this is the selection you want to put on it. You're not a fan of pulleys? You're not an Atwood's force enjoyer? Atwood's machine enjoyer? Okay. So this is interesting. I think we actually just did part B too. So it says, consider a scenario where the block travels in a path with stretch a distance d from its unstretched strength L. Determine expression for the magnitude of the net force exerted on the block expressed in terms of this. Okay. Well, we just said this, right? So F is equal to just K times D. So that's okay. Yeah, it's just K times D. Are you allowed to just say that? I think you just say K not D, right? Yeah, okay, cool. This is fine. Done. Okay. That was simple. Oh no, mods. Zeus. There, I'll pull them out. There you go. Okay. Okay, cool. Right? Good. Yeah, thanks, Dark. You're good. I know, Dark. I run a pretty big Discord myself. Not as big as you guys. How many users do you guys have? I think it's like, it must be 100,000 or something, yeah? 170K. Wow, damn. Yeah, mine's like 2K. But yeah, I have to have mods because someone's always like posting dick pics like in my chats. I'm like, chill. Kids. They never change. 100,000 desperate students. Yeah, okay. All good. Well, at least you guys are wanting to do something about it. That's cool. Does this make sense? F is equal to KD? Yeah? Let me know. We kind of already derived it. It's like beating a dead horse. Okay, cool. All right, derive an expression for the tangential speed. We also just did that. That's literally what we did here. We just mv squared over r is equal to k times delta x, and then we plugged things in. And so, yeah, cool. V is then equal to the square root of k d squared plus dl over m. Tangential, yeah, that's just, that's, okay, so in circular motion, tangential, this you'll learn this in calculus. This is what's called a tangent line. This is tangent, okay? Tangent means it only hits it at one point, and it's kind of like where the thing would be going if you just let go of whatever was keeping it going in a circle. So this is called like tangential velocity. Tangents suck? I like tangents. Tangents are cool. You'll learn in calculus, that's where like derivatives come from. They're pretty cool. So there you go. This is tangential velocity. Yeah, so if for instance you were here and then like suddenly like the thing snapped, you would like keep flying this way. That's what they mean by tangential velocity. It's like the velocity where the thing is trying to go. Yeah. Okay, cool. All right, let's see. And then what are they saying here? Part C. Does your equation for the tangential speed of block B agree with your reasoning from part A? Well, what do we do in part A? Let me go all the way back here. Oh, here. Okay. We said, yeah, we said here, right, that V1 was less than V2. I mean, yes, it does. And that was because, right, as D goes up, V goes up, right? So we say, you know, if D1 is less than D2, V1 is less than V2. There is no tangential acceleration. Yeah, no. There's no tangential acceleration. That gets into torque. That's a whole other thing. Oh, you saw the centripetal acceleration from pointing the center. No. Tangential acceleration. You got to think like, what's providing that tangential acceleration? Yeah, that's a weird one because I mean that technically there has to be then a force being applied in the tangential direction. So it is gonna, but it is also going to change the centripetal acceleration because the centripetal acceleration, right, is directly related to v squared over r. So if this is changing and going up, this is also going to change and go up. Yes, the object's spinning faster. Yeah, the object starts spinning faster. That's what it does. Ooh, next one is your favorite, guys. Yeah, who said this was their favorite? Love this. It's the pulleys. No. No. And it's also not a massless pulley. Oh no. That sucks, dude. Like, what's gonna happen? No. Yeah, I just sometimes want to hide when this happens. I'm just like, I don't really want to deal with this. But okay, we have to. It's inertial constant times the mass. Yeah, it's not that bad. All right, here we go. All right. A block of unknown mass is attached to a long, lightweight string that's wrapped around several turns around a pulley. Blah, 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 blah. Okay, cool. Moment of inertia is that. Oh, dude, how did the dick guy get back? Oh, man. Yeah. Yeah, Dark. There you go. Thank you. Ban evasion? Yeah. Wow. Good. All right, thanks. All right. Determine an expression for the magnitude of the acceleration alpha d of the disk as the block travels downwards. Explain it in terms of all this. Okay. This is where I usually like to, again, rotation and stuff is not that bad if you realize that it's all related to each other. So I like to, I'm going to give a little quick mini lesson here because I know this is probably messing some of you guys up, okay? We're going to talk about like linear and rotational, okay? So let's remember that we have some equations, right? We have x is equal to x naught plus v naught t plus 1/2 at squared, okay? In terms of rotational kinematics, this is theta is equal to theta naught plus omega naught t plus 1/2 alpha t squared. They look almost exactly the same, right? In this case, x gets substituted for theta, v gets substituted for omega, and a gets substituted for alpha, okay? So the movement of something, the kinematics of something moving in a circle, the fish symbol, yes, yeah, is related exactly to the linear one. And then there are some cool things here, all right? So for instance, delta x, which we could think about as like the arc length, is equal to r times theta. V is equal to r omega, and a is equal to r alpha, okay? As long as all of these things are in radians. Yeah, you gotta make sure everything's in radians, okay? Don't put things in degrees. Don't do it. But this is how like the two relate to each other. And then we also have some things such as forces, right? So here we have like force is equal to mass times acceleration. In rotational motion, that is torque, which is equal to I alpha. So in this case, mass is kind of the same thing as I, and acceleration is kind of similar to alpha. It turns out the actual relationship is that alpha is r, that A is r times alpha. Y multiplied by r, force times r per perp. Yeah, you could say that too. Yeah. So this is also F perp times r. Do you see how, yeah, it's kind of also, right? Do you see how like this factor of r just converts things over? Yeah, cool. Y multiplied by r. So this comes into play with, let's say, for instance, you had a circle, right? And you wanted to find the velocity, right? Do you see how that would be equal to the distance divided by the time? And like, what's the distance to go around something, right? That's equal to 2 pi r, right? 2 pi r is the distance to like go around. Yeah. So velocity ends up equaling like, right, 2 pi r over the time. And yeah, it's kind of cool. This, watch, if you move this under, right? Let me think. I want to do this. Yeah, v over 2 pi is equal to r over t. And then I think I want to do this. Oh, okay. 2 pi r is 1 over t, which is the same thing as 2 pi r divided by v. 1 over the time amount it takes for something to go around is also called the period, right? And I think you probably remember, right? Period is equal to 1 over f, and 2 pi f is equal to omega. So omega is equal to f over... This is just a fun little math. I want to show you how it's like all connected, right? F is equal to omega over 2 pi. So if you plug that in, you get that 2 pi r over v is equal to 2 pi over omega, right? And so look, these cancel. And you get that r times omega is equal to v. This is where it all comes from. If you want to know why the relationship is r omega is equal to v, you can... They call this like a back of the envelope derivation. You can do this like on a back of an... no one uses envelopes anymore, but back in the day they used to. This is a fun little derivation for where it comes from. Anyways, not necessary for this question. All right, so let's go back to here. Okay, determine for the angular acceleration as the block travels downwards expressed in terms of this. Okay, very cool. So I know, right, that the angular acceleration is going to have to be equal to the torque, right? Or torque net, right? So net torque must be equal to I times alpha, right? Okay. So we need to figure out what are the torques on this pulley. Okay. And we have the tension. Okay. So on the pulley, right, you have the force of tension, right, being pulled down from the block. Because the block has its own... Here, let's use a different color for the block. Let's do this. So I like to think... Let's just think just about the block, right? The block has... there we go. Has a force of tension pulling it up, and it has a force of gravity pulling it down, okay? That force of tension in the block pulling it up is the same force of tension that's on the pulley pulling the pulley down that way, right? And then, yeah, I think, yeah, you got it there, Dyfus. This is going to be R, right? Okay. So if we look at the torque, right? The torque on this object, that's going to be equal to Ft times R, right? Because remember, torque is also F perp times the radius, okay? And that, okay, has to be equal to I alpha. They told us what I was, right? I was 1/2 mr squared. So you're going to have Ft times R is equal to 1/2 mr squared times alpha, okay? So this goes away, this goes away. You get 2Ft over mr is equal to alpha. Let me see if that's right. Curious. Yes, cool. Yeah, we're good. Does that make sense? I know I went through it a little quickly. I've been drinking coffee today, but I can go through it slower. Yes, I can totally explain it again. Let me do it again. Okay. All right. Let's consider the situation here, okay? This thing is going to want to rotate this way, right? Because this block here wants to fall down. Let's consider what the forces are on this block. It's always good to just like isolate, be like, I am just going to look at this. What is happening to this? I have a force of gravity, right? Which is pulling the block down. And I have a force of tension, right? Which is trying to keep the block up. Yeah, you're welcome. You're welcome, dude. So this is like the force of tension, okay? Now, this force of tension in the rope, this is the cool thing about tensions in rope. Wherever the force is on one side of the rope is the exact same and opposite direction on the other side of the rope. So if this tension is trying to pull the block up, that same tension is trying to pull the pulley clockwise in this case. Yeah, sorry. So if we look at the pulley system, right? I'm going to call the pulley the blue, right? This is also going to have the same force of tension trying to pull it this way. And that is located a distance R away, right? This is also R, okay? So if we consider on the pulley, right? We know that the torque is going to equal, right, the sum of the forces times what we say, or we say the perpendicular forces times the radius. There is only one perpendicular force here on the pulley, and it's the tension. Technically, there's a normal force and a force of gravity from there's a force of gravity on the pulley pulling it down, and there's a normal force of the axle pulling it up, but the R there is 0. So those do not contribute torques. Like, those don't cause the pulley to rotate. Like, the pulley just chilling there. Yes, gravity's pulling it down. Yes, the axle's pulling it back up, but there's no radius there, so it doesn't move it back and forth. It doesn't move it, sorry, it doesn't rotate it. Okay, so this is the only torque you have on it, which is going to be this Ft times R. So we're going to use the big R for here, okay? We're going to say, okay, cool, Ft and R. That's equal to the torque. I also know that torque is equal to the moment of inertia times the angular acceleration. That's what we talked about over here. This is kind of the equivalency between linear and rotational motion, okay? Are we good to here? Is this good so far? Cool, all right. And then I, let's remember from what they said, was 1/2 mr squared. So I'm going to have Ft R is equal to 1/2 mr squared alpha, okay? Now this is algebra, okay? I can cancel out one of the R's. I can put the 2 over here, right? And then I can put the m over here. And then, whatever, this is, one of these is gone, so then this is on the bottom. So you end up getting that alpha is equal to 2Ft over mr. Yeah? We're good? Yup. Okay, sweet. Nice. Okay, let's keep going. All right. That's part A. Not so scary yet. Uh-oh. Oh, man, now they're doing a hoop, dude. Chill. I don't really want to do this. Okay, here we go. All right, here we go. Okay, 2 different pulleys. All right. In both scenarios, pulleys are at rest. Okay, so one has a lightweight stream and mount a horizontal. What's happening here? Sorry. Oh, it's a hoop. Okay, so one of these is a solid disc, and one of these is a. How would you find the force of tension? I think we're gonna solve for it later. Let me see if we do. Oh, we don't. Oh, interesting. Oh, if you wanted to, yeah, sorry, if you wanted to solve for the tension. Wait, what was this? Oh, this was something else we were doing. You would have to use. You'd have to know the gravity. You have to know the acceleration, I think. Well, okay. Here's what you'd say, right? You'd say that force of gravity minus the force of tension is equal to the mass of the block times the acceleration, right? So this gets you mg minus Ft is equal to ma, right? And then you also know from this, from what is it? From this equation, that like Ft times R is equal to 1/2 mr squared alpha. Okay. And then, okay, this is a cool thing. You can replace alpha with A over R, because remember that A is equal to R alpha, right? So A over R is equal to alpha. So this gets rewritten as 1/2 mr squared A over R, right? So this goes away, which is cool. Oh, and also this is the mass of the pulley. Sorry, this is the mass of the pulley. This is the mass of the block. So from that, okay, so if you have mass of the block G minus Ft is equal to mass of the block times A, and this you have what's that? Ft big R is equal to 1/2 mass of the pulley times AR, or times RA. You would need a couple things. Well, I assume they'd give you the masses. They give you masses, that's cool. The Ft is unknown, right? So you would either need the acceleration or you need, or actually you could solve for both. I take that back. This is cool. This is a systems of equations. You don't need Ft actually. Because you have 2 equations and you have 2 unknowns. You need the masses. You have to have the masses. But once you have the masses, Ft is an unknown variable, and then A, The linear acceleration is an unknown variable. The cool thing is that the linear acceleration of this block is related to the rotational acceleration of the pulley. So this would be your systems of equations, and you could just solve for ft and a. That's algebra at that point. Use a substitution method, whatever you want to do. Yeah, but luckily they don't ask you for that here. Okay, they're saying consider consider one that's a solid sphere and one that is a hoop. Okay, in both scenarios, the pulleys begin at rest. Both strings are pulled the same constant force Fa for the same time interval delta t, causing the pulleys to rotate without the string slipping. After the time delta t, the change in angular momentum is equal. Okay, so the change in angular momentum is the same. They're telling us that. So we say like delta L is constant, or delta L1 is equal. I like to just write down sometimes like in equation form what they're saying to me in words. L is angular momentum, and we're going to remember that L is equal to I omega. Is it moment of inertia times omega? Yeah. Okay. Okay. But the change in rotational kinetic energy for the disk is greater than that for the hoop. Okay. So let's remember that kinetic, let's say energy kinetic rotational EKR, that's 1/2 I omega squared. Okay. Interesting. So they're saying that like L1 equals L2, but delta E, let's see, the one for the hoop is greater than, so delta E1 is greater than delta E2. If we define this way, yeah. Okay, considers one, and then in a clear, coherent paragraph length response, what? Is it an English essay or something, dog? What? Explain why the change in angular momentum of both pulleys is the same, but the change in rotational kinetic energy is greater for the disk. Ugh. Okay, fine. I gotta think. Yeah, bro. I'm like, bro, what is this question, dude? Let's see. This is puppy. Okay. Okay, so we have to consider like what the moments of inertia are for different things, right? So the moment of inertia for the hoop is more than the moment of inertia for the disk. I wonder if that's given to you. Do they give that? Do they on the equation sheet? Do they give you moments of inertias for things? They don't. Okay, that's annoying, because then you'd have to know that. I can explain why that is. There is an intuitive response to it. Okay, so little side lesson here. Okay, for like moments of inertia. This one you should know the basic one for a point charge. Yeah, and I'll explain why. Okay, so let's remember, if something is moving around in a circle, right? Like let's say something is like rotating this way. Let's say it's just a point mass. Do you know what the moment of inertia is for a single point mass? MVR, close. It's mr squared. It doesn't depend on velocity actually. Yeah, that's okay. Yeah. So a point mass is mr squared. Okay. Notice that inertia, right, goes up as the radius goes up. All right. Did they say these were the same mass? Yes. Okay. They say they have the same mass, so I'll explain why this is. Okay. So notice that like the moment of inertia goes up as mass starts going further out, right? Okay. So if we had, for instance, a solid sphere of mass m versus, let me do it this way. Yes. I want this to be white. Let's say a hoop. Okay. Yeah, no, the momentum of a point mass is mr squared, but I want to show you that when you find the moment of inertia of something, there is a calculus way to do this. It involves something like, I think it's like mr squared dm over the integral of dm is how this works. Or no, it's mr dm over integral of dm. But basically what you're doing is you're adding up where all the masses are located. So for the solid, yeah, no thanks. It's okay. You'll do it in later physics. Okay. So for a solid disk, okay, notice how you have a lot of the mass is actually located towards the center, right? This is where R is small, right? Whereas for the hoop, okay, if it's the same amount of mass, all of the mass is concentrated towards the edge where R is big. Okay? So this is why the moment of inertia is equal to a bigger mr squared, whereas here it's only equal to 1/2 mr squared. It has to do with like adding up point masses. Well, you're basically thinking about like just adding up like a bunch of different point masses. This is how the calculus works. You're just adding up a bunch of mr squareds. And in the case of the solid disk, some of those mr squareds are located at very small r's, so they don't really contribute as much to inertia. With the hoop, if it's the same mass, right, most of the mass is located on the edge where r is big, which means that the moment of inertia is also going to be big because you're adding up a lot of these big things. That kind of makes sense? Why this one is bigger than this one? Yeah, because they said they're the same mass. All right. Okay. So, okay. So I say I of hoop is bigger than I of disk. Okay? However, right, we said that L of hoop was equal to L of disk. Right? We said this was bigger? Right? L of the hoop is bigger than L of the disk? Okay? Or sorry, L of the hoop is equal to L of the disk. Sorry, angular momentum is the same for the hoop and the disk, but the moment of inertias are different. So then I hoop, W hoop has to equal I disk, W disk. Okay? If this is bigger, what does that tell you about omega? Yeah, I'm going to show you why. Why would momentums be the same? They're different? Okay, because the omegas have to be different, right? So this is bigger, but this is smaller, right? Like compared to this, right? If this is bigger than the eye of the disk, then omega has to be smaller than the hoop. Sorry, omega of the hoop has to be smaller than omega of the disk. Right? Okay. And so if we consider the rotational kinetic energy, right? E is equal to 1/2 I omega squared, right? So notice how the energy is very dependent on omega. Like this goes as omega squared. So if this has a greater I but a less W versus this, because this is omega squared. Oh, E, sorry, this is rotational kinetic energy. Okay. So, because for the hoop I is going up, you would think the rotational kinetic energy would go up. However, omega is going down by the same factor, and in rotational kinetic energy, that's an omega squared. So, we know what I of the hoop is, right? I know I of the hoop, right, is equal to mr squared, where I of the disk is equal to 1/2 mr squared, right? So that tells me this is going up by a factor of 2, right? The inertia of the hoop goes up by a factor of 2. What does that mean the omega of the hoop has to do compared to the omega of the disk? Good. It has to go down by a factor of 2, because remember, these have to be the same, right? So here, right, I have mr squared W hoop has to equal 1/2 mr squared W disk, Okay? If you remembered exactly like what the MR squareds were, this is what it would be. In general, you can just know that this is big, this is small, but let me show you algebraically how this works, right? So that tells me, right, if I cancel these things out, right, MR squared goes away, right? I get that omega of the disk is equal to 2 times omega of the hoop, okay? So good. So the disk has twice the omega of the hoop, right? So if we look at kinetic energy, right, between the hoop and the disk, right? So let's say, so E of the hoop is going to equal to, right, it's 1/2 times, this is MR squared times omega hoop squared. And then E of the disk, or sorry, yeah, is equal to 1/2 MR squared, and then omega of the disk squared, okay? But look at this. So if we compare the energies, right? Yes, the disk has less inertia than the hoop, right? It has half of it. But its omega, remember the omega of the disk is twice that of the hoop. So this is going to go as doubling squared, which means that this will go up by a factor of 4, even though this goes down by a factor of 2. So the energy of the disk is actually twice that, the energy of the hoop. You don't have to say exactly what it is. They're not expecting you to memorize what the moments of inertia are. You just have to remember that a hoop has a higher moment of inertia than the disk does. Yeah, if you're confused, let me try to go through it again. This is probably one of the harder questions. Is this the 25-minute question? Yeah, now you have to say it. Yeah, I'm not going to say it. I'm not going to write that out. That's a lot of stuff to write. Here, we can see what their response was if you want. Yeah. Oh, no, don't need the circle. Yeah, this is what they say. You can use equations, totally. So they talk about this. They say, right, energy is 1/2 I omega squared, right? And then they say omega is related to the moment of inertia, sorry, equal to the angular momentum over the moment of inertia. So this is kind of what we said, right? We said L is equal to I omega. They go straight for it, and they just say, oh, well, omega is equal to L over I. So if these things are the same, right? If this goes up, this goes down. And then they're saying, okay, well, looking at the kinetic energy, right? If this goes up and this goes down by something squared, which means it's going to go down even more than the I that's bringing it back up. Yeah, exactly. I agree too. Yeah, you can just write equations. Like, for instance, I feel like just writing this would be enough as a paragraph because the reader can tell what you're saying. Like, as long as you state I of the hoop is greater than the disk, but the L's are the same. So if one goes up, the other has to go down. This is kind of what they explained when they say omega was equal to L over I, right? This goes up, this goes down. And then you show with the energies that if one thing goes up and the other thing goes down, because this is going down squared, it's going to affect it more. This is where like kind of we start looking at the math and we start trying to, again, relationships are very important with math and physics. It's a lot of like, if this goes as something squared, does this go as the square root of this, or does this go linearly? So it's important to develop that skill of trying to compare things. Yeah. Makes sense? Yeah? I know this one is confusing. This one, they were kind of mean with this one for sure. Is there a part C to this? No. Okay, good. And let's see, is this the 20... Oh, this is only the 13-minute question. Oh, we still haven't hit the 25s yet? Oh, man. Where were the 25s? Oh, the 25s were beginning. Oh, we already did the 25s. Oh, nice. Okay, these are supposed to be short. What's up, Artran? Good to see you, dude. Okay, let's see. Where do you send in questions? Oh, just hang around. I'm going through the FRQ right now, Artran. But afterwards, I'll take individual questions from people and I'll go through them. Yeah, that's cool. Yeah, that's a good rotational one. I know the one you're talking about. Yeah, see if you can post whatever pictures or something. Yeah, I know which one you're talking about. Or I'll go find it. I know where it is. Yeah, I know where the question is. I'll go find it. Okay, a rod with a sphere attached to it. Oh my gosh, what? What type of... Is this a plumbus? What is this? Yeah, thanks. Okay, cool. Got it. Yeah, let me grab that real quick. Let me grab this question. Cool. Nice. All right. Yeah, that's a good one. We'll go over that one later. That's a good one for rotational motion. Okay, a rod with a sphere attached and is connected to a horizontal mount and balanced so it rests in the position upwards from the scale. The center of mass of the rod sphere system is indicated with an X. Okay, that's the center of mass. Okay. The sphere is lightly tapped and the rod sphere system rotates clockwise with negligible friction about the axle due to the gravitational force. A student takes a video of the rod rotating from the vertically upward position to the vertically downwards position, shows all 5 frames. So these frames are not equally spaced in time. Okay, so they're like knocking this thing, and this thing is like falling down, right? Just going down that way. Yeah. Okay, cool. Let's see what happens. What's the question? Okay, cool. Let's see. Not this one yet. Okay. They say... Okay, well, here, let me put this on this one. Use the frames of the video shown to answer the following questions. In which frame is the angular acceleration of the rod sphere system the greatest? Justify your answer. Okay. Okay. Let me think. Do I want to use torques here? I think I want to use... R alpha is equal to A. And I want to use like potential. So here, right, we have the max potential energy. Gravitational potential energy. Because a lot of the center of mass is located very high up, right? Yay, torques, yes. And then here we have the minimum potential energy. We could use the parallaxis theorem, okay. But I'm looking at like energies in this case. So I have MGH, great for the top. And then the radius and the weight force is the most perpendicular. Okay, cool. Minimal potential energy. We'll see. Oh, this is where, okay. Okay, very cool. Well, I already answered this one. This is probably going to be the bottom, is what I would say. Yeah, right. Right, yeah, we already know this one. This one's going to be bottom. Yeah, that's going to be this. Okay, but angular acceleration is different. Okay, so let's remember. Angular acceleration, right, so R alpha is equal to A. The other thing we know, right, is that torque is equal to I alpha. Okay? So torque over I is equal to alpha. So I does not change, right? I is the moment of inertia. That does not matter where this thing is rotationally wise, but torque does, okay? And let's remember that torque is equal to F perp times R, all right? So we need to see like where the force is acting on different things, all right? So there's always a force of gravity pointing down from the center of the mass, okay? So this is what we call like FFG, okay? However, this is R. Okay? So if we want to calculate what the torque is, all right, we have to look at what the perpendicular force is. Yeah, you don't have to do the no, you don't need the parallel axis theorem here. You don't need it. Yeah, it's okay. So if we want to look at like what the perpendicular force is, right? That is going to be let me draw like dashed lines. That's going to be this amount. Uh-huh. And this has like none. Yeah. Yeah, okay, so let's remember, torque, right, is the perpendicular force to the radius. And so we want to look where is the torque the greatest between these two situations, okay? Let's remember that the force of gravity never changes, right? The magnitude of this thing never changes. The magnitude of the radius never changes. The dotted line, yeah, good. The dotted line is what I'm calling F perp. It is the amount of the force of gravity which is perpendicular to the radius. Does that make sense, Felix? So in this case, right, only this part of the force of gravity is pointing perpendicular to the radius. Here, all of the force of gravity is perpendicular to the radius. Here, again, only some of it is, and here, none of it is perpendicular to the radius, right? All of it is parallel to the radius at this point, right? So what we would say is that the maximum torque is going to occur at figure C here, right? And so if the maximum torque occurs there, right, that means the maximum angular acceleration happens. So for this, you're going to say frame C. Okay? Does that make sense, guys? Yeah? Again, when I see these types of questions and I don't really know what to do, write down equations that are involving what the words are saying. So they said angular acceleration. I'm like, cool, angular acceleration, alpha. What do I know about alpha? I'm like, okay. Well, I know that I alpha is equal to torque. Okay? And then torque, right, is equal to F perp times R. I'm like, what is changing here, right? R is not changing as this thing rotates, but F perp is. So the amount of force that is perpendicular to the radius does change because the angle changes. Yeah, exactly. F does not change. F is the force of gravity. That is constant, but F perp does change. Yeah, Fembox. Torques. That's where it comes from. Because sine theta is largest. Yep, good. Yep. Okay. And then for this one, right, rotational kinetic energy is the biggest down here. That has to do with, UE plus KE, right, is constant. So when this drops, this goes up. So when you have the least gravitational potential energy, which is right here, you're going to have the most kinetic energy, and all that kinetic energy is going to be rotational. Yep, exactly. Good. Okay, let's go to... Okay, now they make things harder. Okay. No, not this one. Okay. The rod sphere system has mass m and length L, and the center of mass is located at a distance 3/4 of L from the axle. Derive an expression for the change of kinetic energy of the rod sphere Earth system from the moment is shown in frame A to the moment shown in frame E. Oh, man. Oh, they really want to get us here, don't they? Okay, so one second. Let me pull frame A in. Okay. So, the change in kinetic energy, right, has to be equal to the change in potential energy, right? So change in KE must be equal to the change in the potential energy, right? Change in kinetic energy will work. Yeah. Yeah, you're very welcome, Lightning. Yeah, they'll post the recording so you can watch it later. You're good, dude. Okay, all right. So we got to look at what the change in potential energy is, right? Let's remember that potential energy. We're almost done. This is the last part of the last question. Is equal to mgh, all right? So the change in the potential energy is equal to mg delta h, okay? Where this refers to the position of the center of mass, all right? So in this case, right, let's just call this like h is equal to 0. Do you see how this would be located at h is equal to 3/4 L, right? And then when the thing drops, right, now h is located -3/4 L, okay? So what was the change in the height, right? So delta h was equal to final minus initial, so it's -3/4 L minus 3/4 L. So that's equal to -6/4 L, which is equal to -3/2 L. Okay? So yeah, 3 over 2L total. Good R-Trend, yep. So that's the change in the potential energy. Is going to be, so change in potential energy, that's going to equal to mg times 3/2 L. And that has to equal the increase in the kinetic energy. Okay. So yeah. Yeah, change in kinetic energy is just this. It's just mg 3/2 L. Does that make sense, guys? Okay, because as the potential energy goes, oh, sorry, I should say delta KE is negative delta PE, right? Right, because KE plus PE is equal to constant. Yeah, sorry, yeah. This is, again, with negatives in physics, you just don't get too hung up on the math being exactly correct. Just at the end, like, does it make sense, right? Yeah, you are correct that, like, technically it's negative and there's another negative here, so that they become positive, but yeah, don't worry too much about that. Yeah. So 3/2 mgl. Okay. Briefly explain why the rod and sphere system gain kinetic energy even if Earth is not included in the system. I don't know, because the what? Even if Earth is not included in the system? Because we don't care about it? What? The Earth isn't moving. Let me see what their answer is. That's a weird question to ask. What? Excuse me. One sec. All right. For indicating that the gravitational force is the external force that does work on the rod sphere system. Okay. That seems like a non-answer to me. But yeah. I would say that the Earth is not moving, right? The potential energy of the Earth does not move. I mean, technically it does, because the center mass of the rod hoop thing is getting closer to the Earth, and therefore the Earth is getting closer to the rod, but the differences in masses is insane, so it's basically zero. But yeah, I guess you can say that because, yeah, the gravitational force does work on the rod sphere system. It's not really the gravitational force comes from Earth. This is kind of actually a not good answer or question from them. Yeah, positive work done by gravitational, which is an external force for the rod sphere system, but it's also done by the Earth. Like, you kind of need the Earth. I don't know why they say, like, if the Earth is not included, but yeah, you can basically say it's the same. It's middle. Cool. I don't like this question. Like, this is bad. They don't write the best questions all the time. Yeah, that one is. That's kind of just memorize the response to that one. I don't agree with their answer or the way they're asking it. It's not rigorous. But for AP Physics 1, I guess it's okay. Okay, cool. All right. Anything about all that? So that's it. That's all the FR. We did all these FRQ questions. Okay, that's all the FRQ questions we went through. Are there any questions about specific ones from here? I know you guys talked about you wanted more rotational questions, so I will do, like, this is a good rotational question that I'll go through that R-Tran has posted. But if you have any other, like, specific questions about physics stuff, I'm happy to do those as well. I got when's my next session at? Sorry, when is it at? Next session isn't for another 2 hours. Okay, so I'll do stuff for like another hour max if you guys want. Otherwise, if there are no questions at the end, we can end it early. But I'll definitely do this one. So let me know. You have a problem? Cool. If you can post a screenshot in the chat, I'll go through it. Also, for people that want more help with this, I have an education startup that I work with that is also offering a free AP Physics 1 course. Let me see if I can show where to get to it. Where was it? Okay, here it was. Okay, yeah, cool. I'll see if I can post these links over in this Discord. They're on my Discord as well. But if you join my Discord, you don't have to. There's a thing where you can click, you want the AP Physics 1 review role. And what we have is, so I don't know if you know Flipping Physics, but Jonathan, he's a friend of mine. We have a bunch of these, a bunch of his lecture notes, which are super useful. So we have like some review sheets here that you can go through. They're good things if let's say for instance, you know, you're really having a bad time with the what was it the rotational stuff. Is this yeah? Flipping Physics is great. Yeah, he's a cool guy. I like Flipping Physics. Yeah, he's cool. Well, that's collisions. Where did he have like rotational motion in? One second, let me find it. No, that's forces. That's potential energy. One sec. There's a bunch of them in here. That's that. Okay, here we go.
Nice.
Yeah. Yeah, good. So if you're having questions about like rotational stuff, he has a bunch of very good review sheets which basically go over the key things that are difficult. And yeah, link to my server. Yeah, sure. That's just yeah, it's whatever this thing says it is. But there you go. I'll post it. Mods, you can tell me if I can't link servers, but like I'm happy to post this stuff in your server as well. Yeah, cool. All right, whatever. Good. Yeah, don't do it here. I won't do it. But yes, y'all have rules. It's totally cool. I'll post these things as well as you want, but feel free to DM me on the side if you want, and I can give you guys access to what these things are. I'm happy to help you. It's all free. None of this is like, you don't have to pay for any of this. We do this free. But these sheets are good. Yeah. Okay. Let me do some of the review questions. Here's another one you got. Cool. Let's do those. Let's do them. Yeah. Oh, and you got a problem there? Good. All right, let's do this. Let's do this. Okay, cool. Someone asked, can you plasma military stuff? Yes, lots of plasma physics. Okay, cool. All right, here we go. All right, solid cylinder, mass M, radius R is this with a centered hole. Cool. A launcher of negligible mass is fixed at a radius R on the cylinder. Starting at rest, the launcher shoots a projectile with mass M and V, causing the cylinder to spin. Oh, cool. Okay. So they have a launcher here, and they're causing this to move. Starting from rest, drive an expression for the speed of the launcher after it shoots the projectile in terms of M, R, V, little m, R, and V. Yeah, you're very welcome, dude. Yeah, for sure. Very good. Cool. All right. So this has to do with conservation of momentum, right? Okay. So we have to say that L before is equal to L afterwards. Okay? And so that means the whole momentum of the entire system, right? So at the beginning, at rest, the whole momentum needs to be 0, okay? Because this thing is not spinning, this thing is not being launched, the whole angular momentum before has to be 0, all right? There's no external torques. There are. I mean, but yes, yeah, well, okay, this does launch, okay? So here's what happens, all right? So the angular momentum afterwards of the whole system has to also be 0. So let's look at like what would happen. So you're gonna have, and remember that angular momentum it's positive for clockwise movement. Oh, sorry, no. Let me think about this. Angular momentum is positive for counterclockwise movement, and it's positive for clockwise movement. All right. So L afterwards, right? That's gonna be negative I of the cylinder times omega of the cylinder. Okay? Negative is clockwise. No, negative is negative is clockwise. Yeah. Counterclockwise is yeah. Well, this thing is going to launch this way, so that's going to be that. Oh, so this will be positive. Sorry. Yeah, you're right. Okay. But the projectile. Oh wait, let's think about this. No. I was right. All right. This is negative. Because when this thing launches, right, this way, it's going to force this to, like, rotate clockwise. So this is negative. And then this is going to be added to having a positive moment of inertia from the projectile right here, which is immediately moving this way. And so that's going to be equal to I of the projectile times omega of the projectile. Okay? So let's use what the equation. So they say that the cylinder has a mass of I is 1/2 mr squared. So you have negative 1/2 mr squared omega of the cylinder, right? Which do they give us omega of the cylinder? They don't. But okay, but remember this, guys, right? So omega, so R times omega is equal to what we call like linear speed. So that's V of the cylinder. All right. Okay, let's see if this works. So omega of the cylinder And that has to be I of the projectile. So the projectile is a point mass, which means it has a moment of inertia, which is equal to mr squared. Okay. Plus omega of the projectile. Okay. What do they want to know? They want the speed of the launcher after it shoots. Okay, cool. Okay. And this all has to be equal to 0, right? Now, omega of the projectile is going to be equal to the linear velocity of the projectile divided by the radius of where it's being located, right? So omega of the projectile is equal to v over r. So over here, we're going to replace this. Here, let me put this all over here. We're going to say this is equal to v over r. Okay? Little r is where the thing is located. Okay, cool. And then we want to know an expression for the speed of the launcher. So this is cool. So we can rearrange this for omega of the cylinder, and once we have omega of the cylinder, we can then solve for what the linear velocity would be of the launcher part. Because if I know how much angularly the whole thing is rotating, then I can figure out linearly how much part of the cylinder is rotating. So let's move this over. So I'm gonna have 1/2 big M r squared omega sil is equal to mr squared v over little r, right? M's are gonna cancel. Oh wait. This is little m. Sorry, we gotta keep track of all our little m's. Sorry, this is little m. Little m. Little m. Little m. Cool. All right, good. R's are going to cancel, right? So you get omega cylinder is equal to mv over r, and then it's over big M. So this is going to go on the bottom. Yeah, the VOD will be posted. The VODs will be posted. I'll upload it to YouTube as well, and then I will post links everywhere. Yes, don't worry. Okay, so and then we move the 2 over, right? 2 little m v over mr. Okay, cool. So this is omega of the cylinder so far. So this is what the angular speed of the cylinder is after the projectile launches. So if I want to know what the linear speed of the launcher is, okay? Let's remember that, the linear speed of the launcher is equal to r times omega, okay? And omega is the same everywhere along this cylinder, right? This whole cylinder moves with a certain omega, and everywhere along the cylinder, omega is the same. But the v, the linear velocity, depends on the radius. So this is going to be equal to r times 2mv over big MR. This is going to cancel. And so you just get 2mv over big M. Is that what the answer was, Artran? Is that what you got? No? What'd you get? What's the correct answer? Tell me. If you have the solution too, send it to me so I can see it. V equals 2 mvr squared over mr squared. Okay. Oh, wait, 1 sec. No, this should be 4. Angular momentum before and after. Do they not do conservation of angular momentum, or do they do conservation of... You did it differently from the solutions? Well, what's the solutions answer, though? Yeah, AFG. I'll do yours next. Oh, wait, whoa. You know why? Sorry, this is wrong. This is little r. I always hate when they should use different variables for this. 1 sec. Yeah. 1 sec. This is little r. Little r squared. Okay, 1 sec. So this doesn't cancel, actually, sorry. Let me see. Yeah, we do the same thing. Okay, sorry. Yeah, I have a slight error here. One sec. It had to do when I was defining this. So I, the projectile, is little m, little r squared. The I of the cylinder is big M, big R squared. And then V of the projectile is V over little r. Okay, cool. I move that over. 1/2 mr squared, omega squared. Okay. Mr squared V over R. So this cancels one of these. Okay. I see. You watch how this works. This is going to work out. It's going to work out. It's cool. So, yeah. This is big R. This is little r. This is V. Right? Yeah, no, you're okay. No, this works. This works out. Okay. So this is mr squared over big R squared. Wait, sorry. R, little r. This is big R. Okay. So this is 2m r squared V over big MR squared. Yeah. Okay, which I think is what you got. Yeah, 2m V little r squared over mr squared. Yeah, cool. This is the same answer here, Artran. But it's the same way. It's the same method. Yeah. Yeah, this is why, I make mistakes too. We're all human. But you have to be very careful when writing out the moments of inertias for things to use the proper M's and R's for what they are. So in this case, it's big R and big M for the whole cylinder. In this case, it's little m, right? And little r for the projectile. Yeah, that's fine. Okay, that works. Cool. All right, AFG, let me do yours. Ooh, Baiju's. I like Baiju's. He's cool. Yeah, he's got some good stuff, this guy. Okay. A particle is sliding down a frictionless hemispherical bowl. It passes point A at time t equals 0. Okay. At this instance of time, the horizontal component of its velocity is v. A bead of q at the same mass as p is ejected from A at t equals 0 along AB with a speed v. Friction between the bead and the string may let TP and T... Okay, cool. At this instant of time, this horizontal velocity is that. Okay, so they're saying that, like, yeah. So Vx is just equal to V. So you have A equals around the horizontal AB with speed V. Uh-huh. Let TP and TQ taken by P and Q to reach point P. Okay, so they're saying, how does the time for this compare to the time for this? Oh. And there's no friction? We assume there's no friction? This is a complicated question because, like, there's a couple things at play here. So first of all, the velocity of this thing, right, is going to increase as we lose potential, right? But also the distance that it has to travel changes, right? Because this arc length is greater than this arc length. Okay. But also, okay, this is a cool thing to remember. So remember, right, that force MA, A only points in the y direction, okay? Because F only points, the net force only points in the y direction. So only the velocity in the y direction will change. The velocity in the x direction should stay constant. Okay. And they're going the same distance in the x direction, right? So I'm tempted to say TP equals TQ. Is that correct, AFG? Is it TP equals TQ? Again, I don't have the solutions to these, so I can't say like 100% for sure, but I'm pretty sure it's TP equals TQ. I can probably find this question actually too. It's already on. What is this? Let me find it. Cool. Yeah, where is it? Okay, let's see. They say TP is less than TQ. Let's understand. Okay. Horizontal displacements of P and Q are equal. Yes, BQ moves along AB with constant velocity V. Good. For particle P, motion between AC will be under acceleration while CB will be under... I agree. Yeah, so it's going to accelerate going this way, but it's going to deaccelerate going the other way. But that's only in the Y direction. The horizontal component of its velocity may be greater or equal to V. It will not be less than V. Obviously, TP is less than TQ. Interesting. But it has to travel a further distance. Huh. Okay. See, my argument would be, okay, but okay, there's an additional complicated part to this, which is that yes, the force of gravity is only in the Y direction, but also if this thing is moving along a this is cool. Actually, this is actually kind of cool when this happens. Because this is moving around in a circle, there's also an additional normal force that points in this way, right? And that's what gives rise to the centripetal acceleration that causes this thing to stay on a circle. So this will contribute to the to Vx. And so it's interesting, the argument they say that like Vx will never be less than V. That's true, because as you get to the top here, right, you still have less mgh, which means you have to have more 1/2 mv squared in here. So yeah, for that reason, TP is less than TQ. It's an interesting question. I don't think they would ask something like that on the AP Physics 1 exam. That's a lot. What's up, gamer? What do you want to say? I'll let you on the stage if you tell me what you want to talk about. Lest I gotta like, it's always kind of risky when I have like people I don't even know asking to like say things. Yeah, you're welcome, dude. Or has Gamer been here for a while? Okay, all right, cool. All right, let's see. Okay. A car is driving on a semicircular racetrack. Its velocity at several points of time is shown below. Which of the following could depict its acceleration at the corresponding points? Okay. So let's remember, guys, right, that centripetal acceleration is equal to v squared over r. And it's always going to point towards the center. Okay? Yeah, Archon, I'll do yours. Okay. So as the velocity goes up, the centripetal acceleration is going to go up. Looking at here, right? It's the tangent. This is the velocity, right? This is the velocity. So notice how the velocity is low here, but it's high here. Right? It's the highest here, actually. I believe so, right? So, well, these actually look kind of the same. So we would expect the centripetal acceleration to be the greatest here and here, which should be, so it's not this. So first of all, centripetal acceleration always points inwards. These do not point, this does not point inwards. Here, centripetal acceleration is pointing inwards, but it's constant, which we know it's not, right?
No.
Because the velocity is changing, so it can't be this one. Here, it's not... Whoop, sorry, one second, let me go back. Here, it's not pointing towards the center, right? Here, it's pointing like off-center. It has to point towards the center of rotation. So it's not this one. It's also not this one, because look how this one, right, does not point towards the center. So it has to be this one. Yeah, this would have to be choice C here, Riva. Because every single centripetal acceleration points directly towards the center, and the magnitude gets bigger as we go around because the tangential velocity is getting bigger too. Does that make sense, Riva? It says the answer key is D. Wait, what? Really? Oh, they want, sorry. They want the total acceleration. Oh, okay, sorry. I read this as centripetal. That's what happens after I've been streaming for like 2.5 hours. I just start reading real quickly. All right. Yes, okay. All right. So centripetal acceleration would always point towards the center, right? Okay. However, there is some linear acceleration as well, right? Because the velocity is going from being in magnitude, right? It's getting bigger, okay? Which means you have some linear acceleration in this case, which is pushing it kind of, so let's look here, right? Velocity is this. Velocity is getting bigger. So velocity got bigger in this direction, so there is some linear acceleration in this direction, which is going to push the general centripetal acceleration a little bit more to the right. And then here, right, okay, centripetal acceleration would point straight in, but we also have linear acceleration moving it at a faster speed up, so that means this is going to push the total net acceleration a little bit up. And then it's the same thing for here, right? Again, centripetal acceleration should point straight this way, but an increase in the acceleration here means there's a little bit more acceleration to the top left, which is why it shifts the net acceleration up as well. Yeah, I read this as centripetal. Again, that's another tricky question. Someone asked that actually earlier on the stream, didn't they, Arthur? I feel like someone asked, like, what happens if, like, if the thing is changing? And then I said, yeah, there is also linear acceleration. Yeah. Again, I don't think they're going to ask that. That's it's good you're asking it. It's a hard question, but I don't they're not going to try to intentionally trick you this way. Like, that's just mean. But yes. Oh, is you while you were solving the question while watching the stream? Cool. Yeah, good. Well, yeah, then that's where this comes from. You're right. Yeah, you're welcome. Okay. Let me see. Archer and another one. Let's pull this in. Okay. A projectile of mass m is shot at a speed v at an angle theta above the horizontal. At the instant it reaches the peak of its trajectory, it collides and sticks to a block of mass m, and the combined mass slides on the table with a coefficient of kinetic friction mu coming to rest on the table. Derive an expression for the distance that the combined mass... Oh, wow. Okay, there's a lot. All right. Okay, so when this happens, you have to, like, define time points. So this is what I'm going to call, like, time 0. This is going to be time 1. And then we have a point where the block thing... Here, let's get a... I can get a screenshot of it. Opponent. Yeah. Where'd you go? Where'd you go, girl? Where'd you go? No. Oh, there it is. Okay. Okay. Now, come here. Okay. And then we have a point where this block is going to slide and then stop. Okay? So this is going to be what we call, like, T2. So it's T2, and this is stopped. All right? And then the important thing is that the energy here has to be equal to the energy here. All right? So the first thing we need to do to solve for is we need to figure out what the energy is when this thing collides into this. So this is interesting. This is a great question because it combines a lot of things. It combines kinematics, it combines conservation of momentum, and then it's also going to go over conservation of energy. So we have a bunch of different parts to this. So the first thing we need to do is figure out what is KE is not conserved from here to here. But KE is conserved from here to here, but there's also the energy lost to friction. Yeah, well, it's weird to say that KE is conserved. Total energy is conserved. Yeah. But yeah, let's see. Okay, so what I want to figure out first is, like, what is the velocity of this ball, right before it hits this. Okay, so let's figure that out. So actually, T0 is really like right here. It's like right before they collide. And then, so I'm going to call this, like, T0. And then this will help me figure out what's going to happen. So we have... Let's first figure out what the velocity of this ball will be when it gets to the top. And it's only velocity in the x direction, right? Okay. So this is v. This is theta. Do they give me the height? Oh, interesting. They say at the peak of its trajectory. Oh, very cool. Okay. So we know at the peak of its trajectory, right, that Vy will be equal to 0, right? So there will be no velocity in the y direction, okay? And Vx will just be whatever this is. This is going to be V cosine of theta, okay? Because the velocity of this block, or no, sorry, of the ball. Sorry, we got a ball. Where's my ball? Okay. The velocity of this ball in the x direction is constant as it moves. Okay? So there's this point right here where we're gonna have the circle, we're gonna have the block, okay? This is gonna have a velocity which is gonna be equal to V cosine theta. Right? Initial velocity, cosine theta gets you the Vx component. And this is gonna have a velocity of equal to 0, because it's at rest, right? And then the two things stick together. Oh, can I just grab both these? Okay. So now they're stuck together. Okay. And they're going to have together some, like, we're going to call this, like, V1. That's time point 1 when these two things are stuck. All right. So what do they give me masses of things? Oh, okay. The block is the same mass as the projectile. Great. Okay. So I know mv cosine theta plus m times 0. This is the momentum for the beginning situation. Has to equal to 2m v1. This is conservation of momentum. So remember that, like, sum of mv has to equal the sum of the mv's. Okay. In this case, the projectile had a velocity v cosine theta. The block had a velocity of 0. So we don't have any momentum from here. And the momentum for the projectile is just mv cosine theta. Afterwards, when they stick to each other, all right, now they're considered like a solid object which has a mass of 2m and is traveling at speed v1. All right, so that tells me that v1 is now equal to v cosine theta divided by 2, right? If I divide that and I divide that, all right? Okay, so now we need to look at the difference between these two things. So this is 2m moving at speed v1, and then eventually, oh no, not that. They're going to stop, okay? After moving some distance d, okay? So here v is going to be equal to 0, all right? And so this is where we have to do conservation of energy. So remember the types of energy we have, right? We have gravitational, we have kinetic, and then we also have, like, energy lost due to friction. Because the block and the projectile are at the same height from start to finish, yeah, work is the same thing. It's the same. From start to finish, there's no change in the gravitational potential energy. So all there is really just kinetic. So here, we have 1/2 times 2m times v1 squared has to equal, now the velocity is 0, right? So that's going to be 1/2 times 2m times 0 squared, plus the energy that was lost due to friction. That's also called the work due to friction. Exactly, yeah, well, no, so why not conservation of mv? Because it's a collision? It is. So we did conservation of momentum here, Felix. That's when I had mv cosine theta, right, of the ball right before it hits the block, has to equal 2m times the new velocity of the block and square system at the beginning when they collide. Got it? Cool. All right. So now I'm doing conservation of energy once the two are stuck together and they're moving. All right. So this is the energy of them together. When they start moving, this is the energy when they stop. Kinetic goes to 0. Potential's the same. There's no change in the height. But there is work done due to... There is energy lost to friction, which is the work of friction. I like to always put this as an energy on the right side, is what I do. So this is going to be energy due to friction, which energy due to friction, remember, is the force of friction times the distance it travels. And the force of friction is equal to mu k Fn. And Fn, for something that's just chilling on a block, just chilling on the ground and whatnot, that's going to be equal to mg. So this is going to be equal to, the Fn here is going to equal to 2m times g. So all together here, you get, so this is going to cancel. You get mv1 squared is equal to mu k 2mg times the distance, okay? Masses are going to cancel. That's pretty cool. Right? We're good? Yeah? Did they give us mu? Mu is okay? Good. Okay. And then remember that v1 was equal to v cosine theta over 2. So this is going to be v squared cosine squared theta over 4. So that comes from this. Good. And then this is equal to 2 mu k g times d. What do they want us to solve for, man? What are we doing? Oh, the distance. Okay, cool. Awesome. All right. All right, cool. So distance is equal to v squared cosine squared theta all over 8 mu k g. That's what it should be. Is that what you got, Artran? Nice, good, awesome, love it. Cool. Nice, yeah, that's a good question. Okay. Yeah, that's what they did. I'm sure they did. This is a good question. I like this because it involves a bunch of different physics concepts. It's kinematics, conservation of momentum, conservation of energy. Oh, they had some follow-up questions. Let's see real quick. Sorry. If the ball bounced backwards instead of sticking, would the distance be greater, less, or the same? It would be less, I think. Well, wait. No, if it bounces, momentum needs to be the same. Oh, I think it would be greater. Yeah. The distance would be greater for a couple of reasons, because now when you do sum of momentum afterwards, this is moving this way, so this has to move this way even faster, I believe. Angry Birds, yeah. Yeah, I agree, greater. And then also this helps out because when this thing is moving through friction, there's less friction because there's less mass. So yeah, that's why it's greater. If the table's height is increased so the trajectory can be with initial speeds of 3v, assuming the collision still happens at the peak, okay, and the blocks stay on the table, by what factor will the distance change? Okay, well, yeah, look at this, right? What was our equation here, right? So if v goes up by a factor of 3, if tides hit, okay. But also, theta's going to change then, right? So if this gets taller, the angle has to go up. So there's actually some interesting things here. So if this is tripled, the distance already goes up by a factor of 9 because of v squared. But then also, there's going to be some change to the angle. Right? Yeah, 9x. I would say 9x. But, I mean, also, you have to assume it's being shot at the same angle as well. Or it's being shot at a different angle. Okay, because distance is related to v squared, Felix. And so if v triples, v squared will 9-tuple, and then the distance goes up by a factor of 9. Yeah? Oh, sorry. That was in the follow-up question they said here. Sorry. They said, yeah. They said, if the experiment is repeated, so the initial projectile speed is 3v. Yeah, cool. Yeah, this is basically like an Angry Birds question. Pretty funny. Okay. Cool. Yeah, that's good. Any other quick questions with stuff before I go? You're welcome. Yeah, you're very welcome. Again, if you need more help, I do free tutoring on Twitch. You have my Twitch. Just I'll be doing Monday, Tuesday, Wednesday. There's a schedule as well. So if you have any like last minute questions you need before the exam, or you want to go over something, feel free to like find me when I'm streaming. So Monday, that'll be 3 p.m. Pacific, 5 p.m. Central, 6 p.m. Eastern, and you can ask whatever, and I'll go through questions just as I did here. I thought this was a good thing to go through the FRQ just entirely because it does cover all the material that you're going to need to really know. And then hopefully you learn something from the strategies that I use in order to, solve different parts of the questions. A lot of things are dependent on like relationships. Like if this doubles, does this triple? If this goes by the square root of this, what is this? So you want to get very comfortable with that. It'll help you a lot with those types of questions. Cool. Okay. All right. Thank you very much for coming. Big shout out. Thanks, Gohar, for having me on this on your stage here to help you guys out. Feel free to find me out. Feel free to find me everywhere else. And if you need help with AP Physics 2, I'm doing a session on that in another hour and 15 minutes. So lots of physics today. You're very welcome. Good luck on the AP exams. You guys are going to do great. Any other questions, feel free to DM me, and you'll find me around. Cool. All right.